Hey guys, welcome back to another video. This video is going to be a detailed crash course for all of the organic reactions for A2 level organic chemistry. We're going to cover everything from reactions of arenes to hydroxy compounds to carboxylic acid and its derivatives and nitrogen compounds. So we're going to talk about all of those necessary organic reactions in this one video, and I'm going to try and make it as convenient as possible to be able to remember everything, right? So let's get started. I know this video is going to be quite long, but we're going to start off with reactions of arenes, right? In this section, we're going to learn about all the substitution reactions that arenes go through. We're going to learn about its oxidation and hydrogenation, right? So let's start off with the section 1, that is going to be substitution. So for substitution, we're going to start off with halogenation. Now, as per the name suggests, it's going to be a substitution reaction with any sort of halogen, right? And this reaction will be a substitution reaction, but an electrophilic substitution reaction. Why electrophilic substitution reaction, you ask? Because look at this. This is going to be your typical chlorine molecule. This is going to be your typical bromine molecule, right? Now, what's going to happen over here is when these bonds are going to be broken, with these diatomic molecules are going to be put apart, what's going to happen is one of them will be charged positive, one will be charged negative, right? Okay. Heterolytic fission takes place, right? One is positive charge, one is negative charge. Now, notice one thing. This is going to attack the benzene ring, right? And after attacking the benzene ring, what's going to happen is it's going to attract the electrons from the ring structure and it's going to form a bond with this ring, right? It's going to form a bond with the benzene. Now, this acts as the electrophile and this substitutes the hydrogen atom, which is why a bond forms, and this is called a substitution reaction. So let's understand this. Now, in case of substitution reaction of arenes, we're going to see it with respect to two main halogens, that is chlorine molecule and bromine molecule. Now, for either of the reactions, you're going to need a catalyst, and this catalyst is going to be AlCl3 anhydrous or AlBr3 anhydrous. So with respect to your halogen, you're going to choose your catalyst accordingly. Great. Now, both of these are going to be anhydrous. Great. Now, anhydrous means dry, basically. So now, why are catalysts needed? The catalysts are basically needed because the benzene structure is very stable. Why, you ask? Because of the ring. Because of the ring. Since the electrons are moving around, and this makes the entire structure very stable because the electron density is equally distributed throughout the structure. So you need the catalyst. Great. Now, in case of halogenation, you're going to be having this benzene structure reacting with the bromine molecule or any halogen, in our case, chlorine molecule or bromine molecule. You're going to use a catalyst, AlBr3. This is going to be anhydrous. And what you're going to see is the hydrogen atom over here is going to be substituted by the electrophile Br+. So after the substitution reaction takes place, this gains the electron from the ring and forms a stable structure with the benzene molecule. Now, this product is called a bromobenzene. If a chlorine was attached, it would be called a chlorobenzene. Great. Now, since you had one bromine ion left, right? You had one bromine ion left, a negatively charged ion, because remember, this molecule was broken and you had one electrophile and this bromine negatively charged with a lone pair of electrons. What is it going to do? Now, what this is going to do is it's going to attract the H plus released, right? It's going to attract the H plus released and going to be attached and form HBr. It's an acid, right? Great. So this is your entire reaction. In this reaction, we have considered a normal benzene structure, not attached to any alkyl group. Great. So this is how the reaction is going to be. The hydrogen atom substituted by the bromine atom, and your product is going to be one bromobenzene and the other an acid, that is HBr. Great. Now, halogenation of alkyl arenes. We worked with a simple benzene structure. Now we're going to work with an alkyl arene, that is, an alkyl group is going to be attached to the benzene structure. All of the other things that have been mentioned in this reaction is going to remain the same. The catalyst, the requirements, the products, all of those are going to remain the same. However, the difference is going to lie within where the bromine atom will substitute the hydrogen atom, right? Now, in this case, what you have is this methyl group, or it can be anything, an ethyl group, propyl group, anything, right? It can be attached to this. Anything can be attached to this benzene structure, right? In this case, I'm taking what? I'm taking a methyl structure, alkyl group attached to the benzene structure. Now, what happens is when this bromine molecule is going to come and react with the benzene structure, now it has only these few places to substitute the hydrogen atom, right? Consider this, that this Br is going to be one positively charged electrophile and the other negatively charged with a lone pair of electrons. Now, where will this electrophile go to? This position, this, or this. Let's number it, right? Let's number it to understand where it's going to go. 1, 2, 3, 4, 5, and 6. Now, what we understand is this Br electrophile is going to displace or substitute the hydrogen atom in only position 2 or position 4 of the benzene ring. Why is that going to happen? Let's see. This alkyl group has an electron donating effect. This activates the 2,4 carbon atoms the most and is ready to give an electron to the electrophile. Great. Now, when you see this 2,4 electron donating effect, what this really means is this alkyl group, alkyl groups in general has a positive inductive effect, or the other way to name it is electron donating effect. So this is going to be a group that donates electron, and it's going to activate these following positions, right? It's going to activate 2, 6, and 4 position. What's going to happen is, due to its electron donating effect, it donates the electrons nearby, and this is going to push these electrons to the 4th position and these electrons to these position. Why? Due to repulsion. So initially there were a bunch of electrons over here roaming around, and since alkyl group is pushing electrons to this position, this is going to repel the electrons initially in this position and put it over here, which is why your Br electrophile, bromine electrophile is going to, positive electrophile is going to come and attack this, and this position, right? So due to the electron donating effect, what we see is the hydrogen atom being displaced, or replaced at a specific position. And in case of electron donating groups, that is an alkyl group in our case, we're going to see the 2, 4, and 6 groups or positions being activated. You can also call this one 2 or this one 2, doesn't matter. It only depends from which direction you started counting, right? Great. Now, what we understand is, in case of an alkyl group present, we're going to have hydrogen atoms substituted at 2, 4, and 6 position. Keep that in mind. Now, same thing is going to happen. You're going to have a bromine molecule being separated, and the electrophile Br plus is going to attack this position, let's say, and it's going to substitute or replace the hydrogen atom and form a bond in this position, or in this position, right? Great. So in all of those cases, you have HBr, an acid being formed. Why? One Br minus left and one H plus being replaced, so they join together and form HBr. Great. Now, in all of these cases, the bromine electrophile is going to replace hydrogen atom at 2 or 4 position and going to give the products accordingly, right? So in the first case where you have the bromine atom replacing the 2 position hydrogen atom, you're going to form 2 bromo, that is replacing the 2nd position hydrogen atom. So 2 bromo and methyl, that is due to this methyl group being present, methylbenzene. Now, according to our syllabus, you're going to respect the alphabetic sequence, which is why I write the bromo structure or group at the front and then the methyl group later, right? So you're going to write it as 2 position bromo methyl benzene. Great. Now in the latter case, I have the bromine atom replacing hydrogen atom in the 4th position. Hence, I'm going to write it as 4 bromo methyl benzene, and accordingly. So in this case, again, if you count from this position as 1 and this is 2, it's also going to be 2 bromo methyl benzene and not 6. It would be 6 if, let's say, there was one here and there was one here as well. But in our case, we don't. Which is why, since you're counting from this position to, it's anti-clockwise, hence you're going to have 2 bromo methyl as well. It's going to be the same thing, right? Because notice one thing, if you flip this, right, you're going to have the same structure as this one, which is why it's still going to be 2 bromo methyl benzene. Anyways, now what's going to happen if the halogen is in excess? More than one substitution may take place. Now, in initial cases, we're taking limiting amounts of halogen. Now, when you have excess amount of halogen, nothing is stopping it from replacing all the hydrogen atoms. That is in the position 2, 4, and 6 only, not the other ones. When you have chlorine in excess, it's going to replace 2, 4, and 6 position hydrogen atoms, all of them. And again, in the presence of this catalyst AlCl3. And since 3 hydrogen atoms hydrogen ions are being replaced, you're going to have 3 HCl, that is 3 molecules of HCl, that is acid, right? Great. Now, the end product that you get, if you take a wild guess, is going to be 2, 4, 6 trichloromethylbenzene. Tri, because you're going to have 3 chlorine atoms attached to your benzene structure, and methyl due to this methyl group. If it was ethyl, then ethyl, whatever group is attached, you have to mention it. And at the end, benzene. Great, that is how you're going to name it. If you had 2 chlorine atoms, it would be 2,4-dichloromethylbenzene. Great. Now, the other important thing you need to understand is the mechanism of electrophilic substitution. Now, the amazing thing is, in case of electrophilic substitution, the same thing takes place again and again for all sorts of electrophilic substitution. So if you understand one properly, you can replicate it with all the other cases. So let's understand this one properly, and we're going to apply that in other cases as well. Fair enough. So step 1, what's going to happen? Keep this in mind. You're going to first form the electrophile itself, right? You're going to have this molecule, as I had mentioned, it's going to break down into one electrophile, and the other Br minus is going to join our catalyst. It's going to join what? Our catalyst. That is the purpose of our catalyst. It forms an intermediate. This AlBr3 is going to gain the bromide ion and is going to form AlBr4 minus, right? AlBr4 minus. And you have what? Your electrophile. This is the important part. And in this first step, after you form the electrophile, it can now attack the benzene structure. Great. So halogen reacts with a halogen carrier, this halogen carrier. In the reaction, Br of the Br2 takes a lone pair of electrons and forms a dative bond with the AlBr3. That is, it's going to donate its lone pair of electrons. This Br minus is going to donate and form a bond, dative covalent bond with AlBr4. I mean AlBr3. So after joining, it becomes AlBr4 with what? A dative covalent bond. Great. Now the two electrons fill the 3p orbital of the catalyst. That you don't really need to know, but I just added it up. Anyways, step 2. You have formed now the electrophile. What's going to happen then? This electrophile is going to attack the benzene structure, the benzene ring. So what you will have is this Br ion, right? The electrophile attacking this ring structure. And it is going to attract the electrons inside the benzene ring towards itself. So it's going to attract the electrons from inside the ring and try to form a bond with the benzene structure. So this electron is going to leave the ring structure and is going to join the Br plus ion, forming this bond, forming that bond, right? So this is your intermediate, the position or step where you're joined to both the hydrogen atom and the bromine atom, right? So you're joined to both, but this is unstable. Since inside the benzene structure, the ring is incomplete. It has a net positive charge. Why, you ask? Because it donated its electron to the Br plus to form a bond. Hence, it is unstable. So what is it going to do? It wants electron again. It wants the electrons again, right? So what is it going to do? By the way, it donates a lone pair of electrons to the Br plus to form the bond, right? Now, what's going to happen now to become stable again is this is going to lose electrons. That is, the hydrogen atom is going to give both the electrons away to the ring structure to again form the benzene ring. Great. Now, this hydrogen atom is going to leave in step 3. So, 2 electrons from the benzene ring forms a covalent bond, dative covalent bond with the Br ion, right? Electrophile. This breaks the ring structure, leaving 4 pi orbital, that is p orbital, electrons and positive charge inside. Therefore, inside the ring, initially there were 6 electrons roaming around. However, due to the dative covalent bond with this bromine atom, now what has happened is it lost 2 of its electrons, which is why it has left our net positive charge inside the structure, right? So it wants to pull back 2 electrons again from the hydrogen atom, right? From this bond. Great. So now let's look at step 3, regeneration of AlCl3 and the benzene ring. Great. So as I mentioned, this hydrogen atom now has to leave the benzene family, unfortunately. And it is also going to sacrifice and give its electrons away, unfortunately. It's going to give a lone pair of electrons inside the benzene structure, that is reforming what? The benzene ring. Great. Now another good thing is also going to happen over here. Remember, our catalyst had to sacrifice and gain a bromide ion. However, now, since you're going to have this hydrogen atom donating 2 electrons and leaving the structure as H+, it is going to meet this bromide ion from this catalyst. This hydrogen ion is going to meet the bromide ion from this catalyst and is going to escape as HBr. These two are going to react together forming HBr and is going to leave with our catalyst. This catalyst, remember, we started off with AlBr3, which sacrificed and gained one bromide ion. Now it has lost that bromide ion to this handsome guy, the hydrogen ion. Great. So at the end of the day, we have reformed our catalyst. And what do you know about catalysts? The catalysts do not deform, right? You're always going to get your catalyst back, and we do. Great. So at the last, we are going to be left with HBr, reform our catalyst, and this product, which is the main thing of this entire reaction, right? Great. Fair enough. So in this case, if you have to explain it, what's going to happen? Heterolytic cleavage takes place between the CH bond. What does that mean? Now, heterolytic fission in case of Br atom, what does that mean? One is going to be left with positive charge, one is going to be left with negative charge. Therefore, there is an uneven separation of charge. In case of homolytic fission, if I'm not wrong, the Br atoms are only going to be separated. There is not going to be any net charge on either of the Br atom. In case of heterolytic fission, or in this case, heterolytic cleavage, you're going to be left with a positively charged hydrogen ion, right? That is the point of this. Great. So this CH bond, it's going to lose the H plus ion, right? It's going to gain the electrons from it and lose the H plus ion, which forms HBr. And this Br minus ion comes from where? AlBr4. Great. Now, again, since the hydrogen atoms lost 2 electrons, it's going to go back to the benzene ring, and this is going to restore the ring structure, or better called as aromaticity. So now, one thing to note is, in our case, what we've seen is substitution reaction with a halogen with a benzene structure, right? Now, we also know that in case of chloromethane, or let's say you have a methane molecule, or let's say an ethane molecule, what's going to happen is, in case of you have UV light and also halogen present, let's say you have Cl2 molecules, due to the UV light being present, which allows the reaction to take place, that is free radical substitution reaction, that is the hydrogen atom, you probably studied it in AS, so the hydrogen atom is going to be replaced by the chlorine atom due to the presence of UV light. Now that we saw happen with ethane structures, right? Ethane structures, or any sort of long chain hydrocarbon, right? Now in this case we are also going to have free radical substitution reaction. However, for that to take place, we need an alkyl group attached to our benzene structure. Where is my writing going? Right. So we need an alkyl group attached to the benzene structure. Why, do you ask? Because the benzene structure, as I had mentioned, is very stable. So it's not going to go through free radical substitution just because there is a bit of UV light there, right? So what you're going to see is, when you have an alkyl group, the hydrogen substituted will be from the alkyl group, not from the benzene. So when you boil this, in the presence of a methyl benzene and chlorine molecule, and you also have UV light, you're going to have one of the H atoms being replaced by a chlorine atom. The other chlorine atom is going to form a bond with the H that had been displaced or replaced, and that hydrogen atom, H plus ion, and this Cl minus ion is going to join together again, forming HCl. Therefore, your free radical substitution happened to the methyl side chain, not the benzene ring, right? Therefore, what we understand, in case of methyl benzenes, you can have free radical substitution reaction. Great. So that was our halogenation reaction, that is substitution reaction of benzene structure. Now quickly I'll add one more thing, that is the features of aryl halides. That is, what is so special about halides being bonded to the benzene structure, right? Now I'm going to quickly go over this such that I can focus on the reactions only in this video. But yeah, the thing is, in case of the chlorine atom being bonded to your benzene structure, something interesting happens. That is, chlorine atom has lone pair of electrons in its p orbital. In what orbital? P orbital, right? It has a lone pair of electrons in the p orbital. So if I show you in the 3D diagram over here, is in this p orbital, it has lone pair of electrons. And notice one thing, this carbon atom of the benzene structure also has a lone pair of electrons, or has a p orbital filled with electrons in this position. Now what happens, notice in the diagram, is this p orbital of the chlorine atom is exactly overlapping the p orbital of the carbon atom of the benzene structure. Now this results in a semi-partial overlap, due to which there is a bit of pi bond taking place, due to which you have a bit of double bond nature between this carbon atom and Cl atom. Due to this partial overlap, you have somewhat of a double bond. Not exactly a double bond, because notice one thing, the electrons are roaming around inside this benzene ring, right? Due to that, there is no pi bond forming, that is, double bond is not forming over here. However, there's a partial overlap and a partial double bond taking place over here, due to both the electron clouds being exactly parallel to each other. What you know, in case of double bonds, you need p orbitals forming pi bonds. That is going to be like this and like this. And in the middle, you have what? Your sigma bond, right? S orbital overlap. Great. Now, in case of sigma bond, the overlap is head-on, and in case of pi bonds, the p orbitals are going to be parallel to each other. Great. Now, granted, you know all of that. You know there is a sigma bond between chlorine and the C bond, that is carbon atom, and Cl is going to have a sigma bond. And on top of that, a partial double bond are featured due to the p orbitals being parallel. Great. So, in summary, this phenomena, that is double bond phenomena, is the result of the partial overlap of the lone pair of electrons of the halogen and the benzene ring. This gives the halide bond a partial double bond feature, right? Due to the overlap, you have a partial double bond feature. And on top of that, what happens is the lone pair of electrons of the chlorine atom in the p orbital is also going to be delocalized into the cloud ring. Now, due to this partial overlap, the electrons are now going to be attracted inside the benzene structure, inside the benzene ring. The benzene ring is now going to attract the electrons from the chlorine atom in the p orbital and is going to delocalize those electrons. So, what do we know now? Due to the partial overlap, we have a partial double bond taking place due to the p orbital overlap. Second thing we know is the electrons are going to be delocalized inside the ring structure. Hence, it's going to decrease the electron density on the chlorine atom attached, right? On the chlorine atom or the bromine atom, the electron density will decrease because it loses its electrons into the ring structure. Great. So that is, in summary, all about halogenoarenes. One last thing I have to add over here. In case of halogenoalkenes, the halogen can be substituted by a nucleophile, that is via SN1 mechanism or SN2 mechanism. You have learned that in AS chemistry. Now, there the nucleophile is going to form a bond with the more positive carbon atom and force the halogen to leave, right? So you have a long chain carbon molecule, let's say. Now, whichever is more positive carbon atom, the nucleophile is going to attack that specific carbon atom. And what you're going to see over there is that chlorine atom attached or halogen attached is going to leave the structure. It's going to leave the structure, right? And the hydroxide ion or any nucleophile will be able to substitute the halogen, right? In all cases, what you're going to see is the nucleophile lone pair of electrons is going to attack the carbocation, right? I mean, this is not exactly a carbocation, but it has a partial positive charge. Hence, the nucleophile is going to attack that carbon atom and is going to replace the halogen. Great. Now, in case of halogenarenes, the entire structure, as mentioned, due to the partial overlap and electrons being displaced into the ring structure, it is very stable and it is very unlikely that it is going to go through nucleophilic substitution reaction. Now, due to this stable bond, you're not going to see the nucleophilic substitution reaction take place very easily. Now, for the nucleophilic substitution to take place, if you really want it, you need extreme conditions, right? For the nucleophilic substitution reaction to be successful, you need high temperature and high pressure, right? However, naturally, it is not possible, right? So I would recommend you look into the SN1 and SN2 mechanism from AS chemistry. I'm not going to cover that in this video, but you should go through that because it's going to be helpful. Now, moving on. This is also going to be an electrophilic substitution reaction where NO2 plus is going to act as our electrophile. So let's see how it's going to take place. So the electrophile is NO2 plus, and what you're going to have is this NO2 plus replacing or substituting your hydrogen atom of the benzene structure. Great. And this reaction is going to take place in the presence of H2SO4 and HNO3. This, why you need this? This is basically going to create your reagent, that is, your electrophile NO2 plus. That is why you need H2SO4 and HNO3. So when both of these react together, you're going to get NO2. That is going to act as your electrophile. And this reaction is going to take place between 25 degrees Celsius and 60 degrees Celsius. And make sure you write concentrated H2SO4 and HNO3. Both of these, mind you, are acids. Great. So those are our condition. And the other thing is, if you have an alkyl group attached, again, same thing, electron donating effect, which is why it's going to direct the substitution to take place at this and this position. Otherwise, all of the conditions are exactly the same. Great. Now, when you have this benzene structure and you react that with HNO3 in the temperature of 25 degrees Celsius and 60 degrees Celsius, and make sure you also write H2SO4 when writing the conditions. You write H2SO4, HNO3, and 25 to 60 degrees Celsius, and make sure you write concentrated acid, right? Great. If you write all of that, you're going to get full marks in the question. Now, where is the NO2 electrophile going to displace the hydrogen atom? Anywhere, literally anywhere. Since there is no directing group over here, it's not going to affect. Now, you're also going to get H2O as your product. Why, you ask? Because notice one thing. You're reacting HNO2, right? Sorry, HNO3, right? Now, notice one thing. NO2 is attached to your benzene structure. So what happened to one of the oxygen, one of the hydrogen, and the hydrogen atom from over here that got displaced? So another hydrogen atom. So easily you can say these are going to form bond together and form H2O, water molecule. So you also get one H2O molecule. Great. And at the end of the day, you get a nitrobenzene. So a nitro group attached to your benzene structure. In case of alkyl group present, what's going to happen? Reacts with HNO3 between 25 to 60 degrees Celsius, and you're going to have NO2 in 2 position or 4 position. Great. And also water as your product. Great. Now, how do we name this? You're going to name it as 1-methyl 2-nitrobenzene. So 1-methyl, 1 position methyl, 2 position nitrobenzene. Great. And you can also call this 1-methyl 4-nitrobenzene. Simple. That is how you're going to name it. The other thing I just added for no reason over here is the other name, that is ortho-nitrotoluene or para-nitrotoluene. This is also, I guess, the industry name for these molecules. Ortho basically means 2 position and para means 4 position, right? And the other is meta position, which is over here, that you're going to learn about in another group attached to benzene structure. In case of electron donating effect, it's going to be ortho and para directing, that is 2 or 4 directing, right? You don't need to know this. Forget about this. So yeah, you're going to have 1-methyl 2-nitrobenzene or 1-methyl 4-nitrobenzene. Great. Now, the question that you probably were thinking about is, what's the point of using H2SO4, right? Now, the point is, the mixture of HNO3 and H2SO4 produces our nitronium ion. This is not exactly nitrogen dioxide, by the way. There is a difference between your double bond structure between your nitrogen and oxygen over here, which is why this is not your nitrogen dioxide structure, because the bonds are not the same as nitrogen dioxide. So this is your nitronium ion. It has a net positive charge. And how do you create this electrophile, guys? You're going to create this electrophile freshly by reacting between HNO3, that is your acid, and H2SO4, that is also your acid. So when you react both these acids together, you're going to get H2NO3 plus and an intermediate HSO4. So what's happening over here? Notice, what is the stronger acid over here? H2SO4. And what it's doing is it's donating its H plus ion, right? It's going to donate its H plus ion to H2NO3. And what that does is it's creating step 2, where this H2NO3 can break down into what? Your nitronium ion, NO2 plus, and H2O. The rest of the H2 and the other O is going to form H2O. That is one of the products over here. Great. Now, the other HSO4, that was your intermediate, that is, it gave its H plus OA to what? HNO3. And this HSO4 is going to now gain H plus from where? From the benzene. Remember, the NO2 will displace or replace the H atom attached to the benzene structure. So this H plus, where is it going to go? This H plus will attach with this intermediate, that is your catalyst. And this catalyst is going to reform H2SO4, that is sulfuric acid. So your catalyst is reproduced, right? So this is your 3-step for this step is actually not necessary. These two are mostly what you need, that is how to form the electrophile. This is the extra step. Anyways, so this is how you form the electrophile, and you might be asked to show the step of how to create the nitronium ion, that is NO2 plus. This is how we create it in 2 steps. Great. So now, what is the mechanism for nitration reaction, right? So same as all other electrophilic substitution reaction, electrophile is going to form, the electrophile is going to attack the benzene ring, and then the benzene ring will again reform. So in short, let's go over the entire thing. You're going to, in the step 1, you're going to write it as electrophile formation, that is your nitronium ion being formed, that is HNO3 reacts with H2SO4 forming H2NO3 and HSO4. So H2NO3 is now going to break down into NO2, nitronium ion, and water molecule. Now this NO2 ion that is produced is going to react with our benzene structure, right? So this benzene structure, notice the ring is going to attract the electrophile and is going to donate a lone pair of electrons to the nitronium ion, and is going to create an intermediate while forming a bond with hydrogen atom and also NO2. So it's going to leave a partial positive charge inside because it donated 2 of its electrons. Great. Now, in step 3, what's going to happen is the hydrogen atom now is going to lose 2 of its electron and donate it to the ring structure, such that the ring reforms, right? The ring reforms and the H plus ion escapes. And where does it go? This goes to the HSO4, right? Forming H2SO4 once again. Fair enough. So that is the entire step-by-step mechanism of what happens in case of nitration. Now we're going to learn about friedel-crafts reaction. Now, what are friedel-crafts reaction? These are basically processes to add a group, alkyl or acyl group, to the benzene structure. That is, this structure, I'm going to add an alkyl group or an acyl group. What is an acyl group, by the way? So acyl group is going to be those. So if I show you the reaction, this is going to be your acyl group. That is C double bonded O to CH3. This function where C is double bonded to O and there is an R group rest of the molecule, this is known as an acyl group. Okay, so now in our case, since we're learning about friedel-crafts acylation or alkylation, in this part we're going to understand why do we need to do this. First reason is, as I mentioned previously, that benzene structures are very stable. Okay, since the structure is very stable, they're unlikely to go through any sort of reaction. Okay, so now when you add an alkyl group or an acyl group, they're more prone to go through any sort of reaction. So the main reason of going through this sort of electrophilic substitution, that is adding an alkyl group by substituting a hydrogen atom, or adding an acyl group by substituting a hydrogen atom, right? In both cases, electrophilic substitution is taking place, and that is to create alkylbenzene or an acyl benzene. So starting off, we're going to see friedel-crafts alkylation, that is adding an alkyl group. Or the conditions needed, let's see. So to add an alkyl group, you're going to use the same amount of carbon atoms that you want to add for a chloroethane or a haloalkane in general. So if you want to add 2 carbon atoms, or let's say better known as ethyl group, that is C2H5, if you want to add an ethyl group with the same number of carbon atoms, you're going to form or take a halogenoalkene. That is, in our case, we're going to take a chloroethane. Why? Because I want to add an ethyl group over here. So 2 carbon atoms, hence I'm using a chloroethane. So it needs to be a halogenoalkene. Keep that in mind. We need a halogenoalkene in case of alkylation. Okay, so we're going to take the benzene structure, we're going to take the halogenoalkene that we want to substitute, and we're going to heat the mixture in the presence of the catalyst AlCl3. You already know this from the previous reactions. And what's going to happen is remember the hydrogen over here. This is going to react with the Cl atom, and is going to form HCl. And the rest of the structure, that is the ethyl group, it's going to be positively charged because the chlorine negative charge at ion is going to leave the structure, hence making this an electrophile, right? So this CH3CH2 plus is going to attack the ring structure and is going to substitute the hydrogen atom. Fair enough. So that is how we are going to add an ethyl group to the benzene structure. Okay. Now, what is the mechanism for this alkylation process? Same as all other electrophilic substitution reaction. Step 1, create the electrophile. That is, notice this chlorine atom is going to gain the electrons because it's going to create this electrophile, that is the ethyl group. So this is the ethyl group that has become the electrophile. Why? Because it gave its electron away to what? The chlorine atom, forming a chloride ion that now went to the AlCl3. How? Because the AlCl3 attracted the chloride ion and formed this AlCl4 minus, where the extra Cl minus ion formed a dative covalent bond with AlCl3. Okay, so this is an intermediate. Okay, now next, since we have the electrophile, this electrophile is going to attack the ring structure and is going to attract the electrons from the ring structure and is going to form this intermediate, organic intermediate, where is going to form a bond with this carbon atom, and it's also going to have a bond with this hydrogen atom. But this is unstable. Why? Because there is a net positive charge inside, because it gave 2 of its electron to the ethyl group to form the bond. And now what this hydrogen atom is going to do is to make the positive charge go away. It's going to give 2 electrons to this benzene structure and reform the ring. So regeneration of AlCl3 and benzene ring takes place. Hence, the hydrogen atom gives 2 electrons away, and the Cl minus ion over here is going to gain the H plus ion and form HCl, AlCl3, and you will have your ethyl group attached to the benzene structure, hence forming ethyl benzene. So now let's talk about the second type of friedel-crafts reaction, that is an acylation, right? What is an acylation? What is an acyl group? It's going to be C double bonded to O, CH3 on one side, and an R group on the other. This is your typical acyl group, that is C double bonded to O. This is the main part over here. So you can call this the acyl group. This R can be anything, Cl, basically anything. But in our case, we're going to use Cl, that is a halide. That is, we're going to use CH3COCl, acyl chloride, better known as. Why are we going to use this? Because this is going to allow us to form the ethanol electrophile. So as you saw, the ethanol electrophile CH3 C double bonded to O, this is going to be your ethanol electrophile. The Cl ion is going to leave this structure, and you're left with this structure, that is CH3C double bonded to O. This acts as your electrophile and attacks the benzene structure, the ring structure, and is going to pull electrons away. Fair enough. So ethanol chloride is going to react with the benzene structure. You heat that mixture in the presence of, again, well-known AlCl3 catalyst. And you're going to add this ethanol group over here, substituting a hydrogen atom from this position, right? That hydrogen atom gains this Cl ion and forms HCl. Now, how do you name it? It's not really needed, but just for your information, this is going to be called phenylethanone. If you remember from AS level, ketones are basically this group, C double bonded to O and R on either side. That is your ketanone, right? And in this case, you have R group, hence ketanone, right? Now, ketone. So ketone group, this is your R group, this is your R group, and C double bonded to O. So that's going to be your ketone group, hence it's called ethanol. Okay. And why phenyl? Because it's, so in general phenols are this structure, OH. So from this the name phenyl ethanol comes. And why ethanol and not propanol or anything? Because two carbon atoms over here, hence ethanol. Ethanol phenyl added as a phenyl group to the benzene structure. Anyways, you don't really need that. The name is not important. You just know that this is called an acyl benzene. That's the important part. Anyways, so in general, acyl group comes in as the electrophile, attacks the ring structure, and is going to form a bond with the benzene structure, eliminating hydrogen ion, which then forms HCl. Okay, so now let's quickly look at the mechanism. I'm pretty sure we're very well known to this mechanism by now, electrophilic substitution reaction. So let's go over this very quickly. This fluorine atom is going to take the electrons away, form chloride ion. It's going to form the electrophile. The chlorine ion goes to AlCl3, forming this. And notice one thing over here. I'm using methyl benzene. In the main reaction, I used a normal benzene structure, but right now, to demonstrate the electron, donating effect, that is your directing effect of any group. So since this is an electron donating effect, where is it going to direct the incoming electrophile? At this position, and this position. So to try to make you remember that, I'm using a methyl group in this mechanism process. So the ethanol group is going to come and attack the ring structure and gain the electrons and form this unstable structure, leaving a positive charge inside. And this hydrogen atom is going to leave the structure. Notice you could also add this over here or over here. That both of those would be all right. I just added it in the fourth position. Any is all right, but it needs to be 2, 4, or 6. Fair enough. So again, at the third step, you're going to regenerate the ring structure. Aromaticity is going to be regained. Fair enough. So the H donates 2 electrons to the benzene ring structure, and yeah. So this AlCl4 is going to lose the Cl ion and form HCl AlCl3. This structure that is going to be called, it's an acyl benzene structure, but basically, if you want to name it, it's going to be called 4-methyl. Why 4-methyl? Fourth position, 1, 2, 3, 4. Fourth position, methyl phenyl, because it is attached to the benzene structure as a phenyl group. And ethanol, why? 2 carbon atoms. And why ethanol? Because this acts as the R, this acts as the R, and this is double bonded to O, hence a ketone. Hence, this is named 4-methyl phenyl ethanol. Not important, I just named it, just so you know. Fair enough. Okay, so I did say you can substitute at this position and 2 and 6 position as well. Yes, it is going to be correct, but apparently this is more abundant naturally. Majority of the products turn out to be in the 4th position, not 2 or 6, but there are certain products where you're going to see they occupy position 2 and 6. It is mostly because there's one group already here, which is why it tends to be farther away from the other group. Okay, so fair enough. So that was our all of substitution reactions you need to know about arenes for now, in this chapter at least. And now I'm going to move on to oxidation process of ethyl group or methyl group or alkyl group attached to the benzene structure. So how does oxidation take place in benzene structures? Notice normal benzene structures without anything attached to it, no oxidation is going to take place. You need to have an alkyl group attached to it. So alkenes do not undergo oxidation when reacted with oxidizing agent. Any long chain hydrocarbon that is alkane is not going to go through any sort of oxidation, right? You know that from AS. However, in alkyl benzenes, due to benzene ring, the alkyl group is oxidized to carboxylic acid when refluxed with KMnO4. What happens is when this alkyl structure is attached to the benzene ring, it is now going to be able to oxidize itself, right? It's going to form what? It's going to form benzoic acid. That is, it is going to form COOH, that is carboxylic acid group. So if I draw it differently, it's going to be like this: C double bonded to OH, right? This is your typical carboxylic acid group. Fair enough. So what's going to happen is you have an alkyl group that is going to be oxidized to carboxylic acids when refluxed with what? KMnO4, your typical oxidizing agent. So conditions are what? Reflux with alkaline KMnO4, right? Why alkaline? Because that is a more effective oxidizing agent. But then you're going to acidify with dilute H2SO4. Why acidify? I'm going to cover that wait. So basically, you have your methylbenzene I'm plating, and I'm adding your KMnO4 oxidizing agent. Heat the process, forms benzoic acid, and a water is eliminated in the process. Why? Because 2H is going to be eliminated from over here, because only 1H over here. That 2H joins with one of the oxygen and is going to form H2O. Fair enough. So this is your benzoic acid. Now note one thing, very, very, very important. Over here, I have a methyl benzene. However, if I had ethyl benzene or propyl benzene, any sort of long chain alkene attached to the benzene structure would still be COOH. You might imagine that it could be CH2, CH2, COOH or something. Let's say this is going to be your propanoic acid. So no, that doesn't happen actually. What happens is any structure, even if it was a propyl attached over here. So let's say this was your CH2, CH3. So let's say this was attached to the what do you call it, benzene structure. What would happen in that case? Even in this case, this ethyl group would still be oxidized to what? COOH. So whenever oxidization takes place of the alkyl group attached to the benzene structure, it will always turn into COOH only, nothing else, right? Keep that in mind. Fair enough. Now the question, why do we acidify it? We basically acidify because when we are adding the potassium manganate, we are adding alkaline potassium manganate, right? So what happens is a salt forms. This H plus moves away and you're left with COONA, that is a salt, right? I guess benzoic something, sodium benzoate, right? Sodium benzoate, if I'm not wrong. So it's going to form a salt. That's my point. Due to alkaline oxidizing agent being used. So to make sure as our product we get benzoic acid only, not the salt, we're going to further acidify our product, right? That's why we acidify the solution. Okay. Now, next part, that was our oxidation. Remember what happens in the oxidation? You need alkaline KMnO4 and you're going to acidify the solution. Make sure to reflux the solution as well. You get your benzoic acid. Okay, that's your oxidation for alkyl groups attached to your benzene structure. Now we're going to look at hydrogenation. Important, very important. What is hydrogenation? Um, from AS again. You have to, by the way, have concepts from AS level, because a lot of questions require concepts from AS level. So read up on AS level stuff as well. So let's say you have C double bonded to C. So this is your alkene structure, right? So what happened in AS is, if you have this alkene structure, you could go through hydrogenation, that is H2 nickel catalyst, and you would be able to break this double bond and add two hydrogen atoms over here, right? So this would again become an alkane from an alkene structure. Okay, so fair enough. So in our case, in case of benzene structures, what we're going to have is, remember, the ring structure is sort of a double bond that the carbon atoms have. I didn't mention one thing in this video because I'm specifically talking about reactions, that all of these carbon atoms are actually sp2 hybridized. Okay, all of these carbon atoms are sp2 hybridized. Note that. In case of C double bonded to C, these are also sp2 hybridized. That is, one s orbital and two p orbitals join together to form this hybridization. You form this hybridization. So even in case of a benzene structure, if you know the molecular formula is C6H6, not C6H12. Okay, so each of these carbon atoms is bonded to one hydrogen atom. Hence, all of these carbon atoms are making 3 bonds to 3 different atoms. And the other partial bond is this ring structure, which is why they're what? sp2 hybridized. Because they are making 3 bonds to 3 different atoms. This carbon atom is bonding to a hydrogen. This is bonding to carbon. This is bonding to carbon. And there's a partial bond, sort of partial double bond inside the benzene structure. That is the ring structure. You can call it a double bond. No worries. But since the electrons are roaming around, we draw it as a ring, right? So these carbon atoms are all sp2 hybridized. Hence, there is a double bond over here, right? So this we can break. Just like alkenes, we can break this bond and form a cyclohexane. That is, we're removing the ring structure. Now, this carbon atom is no longer attached to one hydrogen atom, but two. It has gotten its family back, right? It has gotten its long lost child back. It has been hydrogenated, that is, added a hydrogen atom. How do we do that? We're going to heat the structure with hydrogen gas and nickel or platinum catalyst. That is from AS. Very simple. Hydrogen, nickel catalyst, heat. Fair enough. Now, what happens if you have an alkyl group attached to it? Let's say methylbenzene. Pretty much nothing. The same thing is going to take place. You add your hydrogen gas. Oh, remember to give 3H2. Why specifically 3? Because this is going to give you 6 H atoms, right? So you need to add 6 H atoms for 6 different carbon atoms. So 3H2. Now over here, same thing. This is going to stay as it is. And you're going to add 3H2. 6, because one here, one here, one here, one here, one here, one here. Fair enough. So 3H2, heat, nickel catalyst, and you're going to have methyl cyclohexane. Fair enough. Okay. Due to the stability of the benzene structure, a substitution reaction is more likely compared to addition reactions, since in substitution the ring is reformed due to heterolytic cleavage. However, in addition reaction, it is not reformed. Cyclohexane is less stable than benzene. So, in case of benzene structures, again, I'm saying it for the third time, benzene structures are very stable. Why? Because of that ring structure inside, which is why they're less likely to go through any sort of addition reaction, because it doesn't want to lose its ring structure, its double bond structure inside, which is keeping the structure so stable, right? So it doesn't want to lose it. Hence, turning it into sp3 hybridized carbon atoms, that is cyclohexane, it takes a lot of effort. It takes heat, it takes pressure, it takes a catalyst to turn it into a cyclohexane, right? So, which is why it's very unlikely to go through any sort of addition reaction. In AS, again, you learned about addition reaction. Let's say you can add OH group and H group as well, right? And make this double bond. However, these are very less likely to take place in case of benzene structures. Fair enough. So that is your hydrogenation. Now, the other thing that I will mention is, just like in case of the ring structure, you have sp2 hybridized. In case of the cyclohexane, you have sp3 hybridized carbon atoms, right? Now, due to this different sort of hybridization, they're also going to have a different angle between this ring structure. In case of, notice, the benzene structure, you can see it literally on a plane, paste it on a plane, and you're going to see it just as this, right? Similar to this at least. And it's going to have 120 degrees of theta or angle between each of these bonds. Okay, 120 degrees of angle between all of those bonds, right? 120, 120, 120, 120, 120. Now, in case of this, which is sp3 hybridized, this is a bit different. Why different? Because this is in 2D, it looks 2D. But when you observe this in 3D, this is not going to be, you cannot place this on a single plane. It's going to have, it is not exactly parallel to all of these carbon atoms. The bonds are not parallel to all the carbon atoms. So there is a difference in theta or bond angle between both the structures. In case of cyclohexane, the bond angles turn out to be 109.5. That is the bonds, that is the carbon to carbon bond are all sort of deviated from a planar structure. These are a bit deviated, which is why there is a theta of 109.5 degrees. In case of sp2 hybridized, they have a theta of 120 degrees. Very simple. So yeah, that is due to different hybridization, they're going to have a different bond angle. Fair enough. Now, for the directing effect of arenes, I'll shortly finish this part. That is, I have already mentioned electron donating group and electron withdrawing group. Now, in case of electron donating group, I already mentioned that is ethyl group, they are electron donating, halides, electron donating, and they're going to activate which positions? If you remember, 2, 6, and 4. 2, 6, and 4. And in case of electron withdrawing groups, that is, let's say C double bonded to O. Remember, this O is very, very electronegative. Plus, there is a double bond. Even worse, it's going to attract electrons towards itself. So, if we have a benzene structure over here and attached this group, carboxylic acid group, this oxygen atom is going to withdraw electrons away from the ring structure. Hence, this is what? It's going to have electron withdrawing effect. And this is no longer going to activate 2, 4, 6 position. It's going to activate different groups. That is 3, 5 position. And this is called meta-directing group. This is a meta-directing group because it is activating which position? 3 and 5 position. So when you have electron withdrawing group, usually C double bonded to O, in those cases, you're going to have electron withdrawing effect. because they're pulling electrons away towards itself. Now, again, you might be confused that aren't halides, let's say, chlorine atoms, aren't they very electronegative? Shouldn't they also pull electrons towards itself? No. Partially you're right, but the thing is, remember I talked about the partial overlap of p orbital. That causes the issue. Due to that, you're going to have that double bond nature, and it is more prone to give electrons to the ring structure. Okay, so that is why the Cl bond with the ring structure is so strong. You cannot separate it because the structure is not polarized. It is very hard. This is not negatively charged. This is not that positively charged. So it's very hard to break this bond because of the partial overlap of p orbitals. Fair enough. In case of electron donating groups, again, they are what? They're going to activate 2,4 positions. And that is pretty much it about arenes. And then in the next section, we're going to talk about what? Hydroxy groups, that is phenols. So, yeah, let's move on to the next section. Okay, so before we move on to the next section, I want to add one last thing, that is, let me make it a bit easier for you to remember the electron withdrawing and donating groups. All of these are electron donating groups. Hence, in the benzene structure, they're going to donate electrons and activate 2, 4, 6 position. NH2, OH, Cl, right? All of these at least have a lone pair of electrons, are going to donate electrons to the benzene structure. Okay, they're going to donate electrons to the benzene structure, hence activate 2, 4, 6 position. Now, these all are very negative and are going to withdraw electrons from the benzene structure. Hence, if this is benzene structure, it's going to pull electrons towards itself. Same with all of these, it's going to pull electrons towards itself, and it's going to notice one common thing: double bonded to O, double bonded to O, double bonded to O, right? It's going to pull electrons towards itself. Hence, these are withdrawing groups, and is going to activate 3 and 5 position. These positions for incoming electrophiles, right? So electrophiles are going to substitute these positions. So these are your electron withdrawing group. Fair enough. So these are all for arenes. And now let's successfully move on to the next section. Now, in this section, we're going to talk about hydroxy compounds. And first up, we'll talk about acyl chlorides reacting with hydroxy groups. So what do I mean by hydroxy compounds? These are basically like alcohols, the hydroxide group added to what? The alkyl chain, making it a alcohol. And in case of, let's say, what you call it, phenols, you have your hydroxide group added to the benzene structure. So these are all hydroxy compounds. Now, we're going to look at the behavior of the acyl chloride first before we analyze the reaction between acyl chloride and hydroxy group. So, what is the behavior of acyl chloride? Acyl chlorides are basically any alkyl chain bonded to C double bonded to O, and in our case we're working with acyl chlorides, hence a chlorine atom also attached to this carbon atom. So this is your typical acyl chloride formula. Now this alkyl group can be literally anything. It can be propyl group, ethyl group. It can be any group attached to this C double bonded to O. So that will change the name. In this case, it is ethanol chloride. If you add one more carbon atom, it's going to be propanol chloride, and so on and so forth. So now, what is the typical behavior of acyl chloride? Acyl chloride easily undergo reactions. That is, it is highly reactive. Now, this is due to the fact that this carbon atom is highly positive, has a high positive charge. Why, you ask? Since it is bonded to two very electronegative atoms, that is the oxygen atom and the chlorine atom, both of which are highly electronegative and pulls electron away. Now, the worst part is there is a double bond, which is why oxygen, it's going to pull far more electrons. So the electron density near the carbon atom is really low. which is why there's a huge charge separation between the carbon and chlorine atom, which is why it is easy to break off this bond, right? Fair enough. Now, that is why it is very reactive, and it is also easy to go through nucleophilic attack. That is, let's say I have OH nucleophile. It is easier to attack this carbon atom since it is highly positive, and it will be more prone to attract a nucleophile. And in that case, it will undergo addition-elimination reaction. We talk about it in more details in the chapter of carboxylic acid and also, I guess, nitrogen compounds. So you'll see what I'm exactly talking about in terms of mechanism, how easy it is, or how in details, step by step, what's going to happen in case of a nucleophilic attack. That is, a nucleophile, any sort of nucleophile is going to join the structure. Fair enough. So this is the typical behavior of acyl chloride, very reactive due to highly positive carbon atom. Now, as the bond of the halogen, chlorine, and the carbon breaks, HCl gas, white fumes will be released. Now, as mentioned, this bond is very weak, so Cl ion, chloride ion, will leave the structure and will bond with H+, forming what? Forming HCl. So we will see HCl gas when reactions with ethanol chloride take place. This is a typical mechanism, but again, we talk about this in far more details in the next section. So yeah, the overall reaction of acyl chloride and alcohol or phenol. So when acyl chlorides, just like carboxylic acid, when reacts with alcohol, will form what? Will form a ester. Via what? Via nucleophilic substitution reaction. The OH acts, the hydroxide ion acts as what? As a nucleophile and substitutes the chloride ion or the chlorine atom. Hence, nucleophilic substitution reaction takes place. Hence, you will see an ester bond forming, that is, an ester linkage will form, just like in case of what? Carboxylic acid reacting with your alcohols. Fair enough. So, in case of formation of ester from acyl chlorides, this is far more fast, and it is also going to give you a larger yield of the product, that is the ester, since acyl chlorides are far more reactive, right? It is far more prone to go to completion. Now, looking at the first reaction, that is alcohol reacting with acyl chloride. Now, when you have this alcohol, ethanol, reacting with ethanol chloride, what's going to happen? Something very simple. This H and Cl will form a bond, that is, it is going to react together and form HCl. And this H plus is going to escape this ethanol structure, and this Cl will escape this ethanol chloride structure. Now, when studying the mechanism, you'll understand it better why it happens. But in short, this HCl will leave the structure and it will form an ester linkage. Now this H, I'm sorry, not this H, I should have drawn it differently. So basically, it should have been like this: H, O, H, and this H over here. So yeah, now it's saturated. So yeah, this H and Cl will form a bond. I mean, it will leave the structure and form HCl, and this O of the ethanol and this C of the ethanol chloride will form a bond, forming this ester linkage. This is your ester linkage, and from this reaction, you'll also get a HCl byproduct that is going to show that it is a condensation reaction, since you're getting a byproduct from this reaction. So this is your ester linkage. How did it form? H and Cl will leave the structure, forming HCl, and this will join this, hence forming the ester linkage, in short. And this is a very reactive reaction, and you're going to see white fumes of HCl escaping. Why reactive? Because ethanol chloride is highly reactive, which is why this reaction is going to be vigorous. So second part, the second reaction is going to be between phenol and acyl chloride. In the previous case, we saw how acyl chloride is going to react with alcohol, but the other hydroxy compound is what? Phenols, right? So what's going to happen in case of phenol? How are we going to react phenol with acyl chloride? Very simple. The condition is, in this case, you need heat and a base. Now, understand one thing. Phenols are highly stable. Phenols are what? Very stable. Due to this negative charge of the oxygen atom being distributed through the benzene ring structure. So the ring is going to pull the electrons into the ring structure, and this is going to distribute the negative charge over a huge area. That means what? That means the negative charge on this oxygen atom decreases, right? So what happens is this makes the structure less reactive, since there is not any high amount of charge residing on your oxygen atom. So this is going to make the phenol structure very stable, and it is not going to go through any sort of reaction that easily. You're going to need reagents and other conditions to make the phenols react due to its stable structure, due to the benzene structure. So you need other conditions, right? What are the conditions going to be to make the phenols react? You're going to heat the structure, A, and the second thing you'll need is a base. What does this base do? Understand. This base is going to remove the H+, deprotonates the phenol structure. Why is that important? So let's say the base you use is NaOH. Now this Na will replace the H+, and this is going to form your phenoxide ion. This forms the phenoxide ion, and this phenoxide ion is a better nucleophile. Why, you ask? Because when you had OH added to this benzene structure, the negative charge on O was less because it's bonding with the H and is losing its electron into the ring structure. So it is not that good of a nucleophile. However, the moment you remove this H, lone pair of electrons, and a highly negative charge, this makes it a far better nucleophile, ready for a nucleophilic attack, right? So this makes it a better nucleophile, right? So we're going to heat the structure and react with a base. Fair enough. So what's going to happen is this OH from the base is going to come in, is going to take this H and form H2O, right? H2O. Now you can add Na over here if you want. That is going to make it a phenoxide salt. Doesn't really matter because in solution the ions are separated, hence the phenoxide ion stays like this. But anyways, this is how you form the phenoxide ion. You react it or put it in a basic solution, I mean alkaline solution, and you heat the structure. And now what's going to happen is this is your ethanol chloride, with which you want to create the what you call it, ester. So this is your ethanol chloride, which acts like the carboxylic acid. This is or was your alcohol. Now it is sodium phenoxide or a salt, or you can just erase this Na+. It's still the same thing. The main point is this acts as the nucleophile. This phenoxide ion acts as the nucleophile. And what's going to happen is this Cl and Na forms a bond. I mean, forms a compound that is going to be NaCl. And this C double bonded to O and this O minus is going to form what? It's going to form the ester linkage. It's going to form the ester, right? So since this O minus is a better nucleophile, it can attack this carbon atom easily. It can attack the carbon atom easily. And the mechanism of these type of reactions, I do talk about it in other, not other video, in other sections. So when you watch the nucleophilic attack mechanism, you'll better understand what's happening over here. But anyways, the main point is the phenoxide ion is a better nucleophile, and it finds it easier to attack this carbon atom and form this ester linkage, right? Great. And the Na and Cl will form this NaCl compound. Now, the other thing I'll talk about is since we are carrying this reaction out in alkaline condition, basic condition, you're getting NaCl. Now, if this was done in acidic condition, you're not supposed to, but in case the question gives a twist or something, if it was acidic condition, you would have HCl, because in that case, this OH would stay as it is. But in that case, the yield of ester would be far less because you're carrying the reaction out in acidic condition. And you know, phenol is not that good of a nucleophile. It's not that strong of a nucleophile due to its stable structure. Now, when it is a phenoxide ion, it is a better nucleophile. Hence, it is easier to carry out nucleophilic attack. So that is in short what's going to happen when you react phenol and acyl chloride. Those are your conditions. Keep that in mind. And this is your ester, right? And at the end of the day, what you get is phenyl ethanoid. Phenyl ethanoid. Fair enough. That is in short the reactions of phenolic structure and hydroxy compounds. Now, the next thing, this is very important. You need to understand this, because a lot of questions, synthesis reactions are going to come from this specific part, and this is producing phenols. Now, to produce phenols, you're going to go through a bunch of organic synthesis steps. So let me start off from the basics. Now, what are phenols? Phenols are organic compounds with OH group attached to the benzene structure. You know that very well. And they can be prepared by reacting nitrous acid, HNO2, and phenylamine. That is, this is your phenylamine. And when you react both, it is possible to create phenols. Now, to do so, we need a bunch of conditions. Keep these in mind, very important. What are the conditions? You're going to need NaNO2 and react it with dilute acid to form HNO2, nitrous acid. You take NaNO2, react with any sort of dilute acid. What does it form? HNO2. Basically, the H plus is replacing the sodium. But anyways, at the end of the day, you get HNO2. Why do we need that? Let's see. Now, after you form HNO2, you're going to keep the temperature below 10 degrees Celsius and then heat the mixture, right? After you formed HNO2, next you're going to heat the structure for the phenol. What do I mean by all that? Let's understand in steps. First step, as mentioned, we're going to form HNO2, right? How do we do that? Notice HNO2 is very unstable. Nitrous acid is very unstable. That is, it wants to go to a more stable state, which is why it is going to decompose, right? Hence, we're going to freshly make it by reacting what? We're going to react NaNO2, HCl with a temperature below 10 degrees Celsius. When we do that, we're going to form HNO2. Very important for the next step. So you're reacting sodium nitride with what? HCl. The H plus replaces the Na, forming nitrous acid, which is not very stable. So we freshly make it, and as a byproduct, we get NaCl, salt. And notice one thing, for this, the temperature is below 10 degrees Celsius. This heat, as I mentioned before, is not for this step, it is for the next step, right? So don't confuse it. For making HNO2 or nitrous acid, you need to have a cold mixture or a cold reaction condition. Fair enough. So this is how you form nitrous acid. Next, what are you going to do? Now you're going to bring in the phenylamine and you're going to react it with HNO2, right? Or nitrous acid in the presence of acidic condition. And what's going to happen now that you keep the temperature between 0 to 10 degrees Celsius, you're going to form an unstable salt. This is going to be your benzene diazonium chloride. This is an azo compound. What are azo compounds? They're going to have typically this functional group. They're going to be azo compounds. They're going to be azo compounds. We're going to learn more about it in a nitrogen compounds section. But in general, what is happening over here? Notice this N nitrogen is going to join this nitrogen, right? So this nitrogen joins this nitrogen atom. What are you left with? You're left with one H atom, two oxygen atom, and two hydrogen atoms over there, and one hydrogen atom over here. Very simply, you're going to form H2O or 2H2O to balance the equation. That is, the 4 hydrogen atoms, 1, 2, 3, 4, and 2 oxygen atom, 1, 2, are going to form H2O. What are you left with? You're left with Cl and you're left with N, which I just mentioned is going to form a bond with this. Great. And that is going to form your azo compound. This is your diazonium salt. Now notice one thing very carefully. This N, nitrogen, you usually know amines or ammonia in general. Nitrogen forms 3 bonds with a lone pair of electron, right? However, notice one thing. Over here, it is forming how many bonds? A triple bond, a single bond, 4 bonds. Hence, a positive charge on the nitrogen, right? And this Cl minus negative charge, right? Fair enough. So this is your benzene diazonium chloride, right? This is your salt. Now, in a solution, you know the ions are separated. So this Cl minus doesn't really matter because it is not exactly bonded to it. In an aqueous solution, it is going to remain as separate ions. Anyways, when you further heat it, that is, remember this, heat. Now you're going to heat the structure. Now you're going to heat the structure to do what? To form the phenol. Once you've formed benzene diazonium chloride that is highly unstable, why you ask? Because of this. Because of the azo group. This is highly unstable, which is why it is now, upon further heating, going to form phenols, right? To do that, what you're going to do is either add water or keep acidic condition. So you take a solution of acid or basically water, and you're going to heat the structure. Heat the mixture. So if you have benzene diazonium chloride, aqueous solution, heat it, and it's going to break down. This NNCl is going to leave and is going to form a more stable structure. In general, every single place, until and unless you add extreme conditions, any compound, any reaction will move towards a more stable state. Every reaction, until and unless you give any sort of external conditions that is beyond the natural condition, it is going to form a more stable state. Now, this was unstable, but what did you need to do? You needed the temperature to be specifically between 0 and 10 degrees Celsius, and that created this unstable compound. Now, when you heat the structure and in an aqueous solution, what's going to happen is it is going to form a more stable compound, and you know phenols are more stable in general, right? Now, greater than 30 degrees is a bit above room temperature. So yeah, you're going to somewhat heat the structure. It's going to be somewhat warm, and what you're going to see is you're going to produce phenols, and at the same time, there's going to be dilute HCl due to this Cl ion leaving the structure and reacting with the H plus ions, and you're also going to get nitrogen gas that is due to this diazo group leaving the structure, right? Hence, you're going to form nitrogen gas, HCl, and a phenol, which is comparatively more stable. Okay, so in 3 steps, first we produced the HNO2, right? Nitrous acid. Second step, we formed the diazonium salt, for which we need the temperature to be between 0 degrees to 10 degrees Celsius. And we formed the unstable diazonium salt. And the third step, upon further heating, this salt is going to break down into a phenol, which is comparatively much more stable, and a byproduct we get is nitrogen gas. That is, in short, how to produce phenols. Now, reactions of phenol. This is important as well. When you have a phenolic structure, you know this OH group is going to have a directing effect. It's going to activate certain groups, specifically 2, 4, and 6 carbon groups. So, phenols undergo multiple reactions due to electron-dense benzene ring, polarity of OH hydroxy group. Now, what I mean by this is, as you know, OH has a electron donating effect since it loses its electron to the benzene structure. Hence, what happens is it activates certain groups, certain carbon atoms. So these are highly, it has larger density of electrons, which is why these are more reactive. Hence, these are going to go through certain types of reaction, more specifically, electrophilic substitution reaction. Now, the reactions it is going to go through is reactions with base, metals, diazonium salts, nitration, and bromination. So, first one, we're going to look at phenols reacting with base. Now, phenols in general, you should already know, act as acid due to its ability to lose the H plus ion. Hence, it is going to act like an acid. Now, phenols are very, very slightly soluble due to the polar OH. However, the benzene ring is non-polar. In general, long-chain hydrocarbons or small-chain hydrocarbons, they are not polar due to similar electronegativity of C and H. Both carbon and hydrogen have similar electronegativity, which is why they are non-polar. However, when you have highly electronegative atom like oxygen, that makes a difference in how electronegative both parts are. That is, benzene structure relatively stable compared to your oxygen atom, which is going to be highly electronegative. So there is a difference in polarity, right? Okay, so that is also why it is going to go through reactions. Now, in our case, this phenol is going to act as your acid, NaOH your base, and typical acid plus base reaction is going to take place, right? What's going to happen? You're going to form a phenoxide salt, that is sodium phenoxide, and OH and H will join together forming water molecule. Quickly, let's move on to the next one. Phenol reacting with metals. Now, these metals need to be highly reactive. Why, you ask? Because phenols are not that reactive since due to the stable benzene structure, but it is still somewhat reactive, which is why we need reactive metals for the reaction to take place. Now, vigorous reaction takes place between molten phenol and reactive metals. That is basically at higher temperatures, it is more likely to go through a reaction due to the heating effect, right? So you also need reactive metals like sodium, Na, and it is going to go through typical acid plus metal reaction. That is, you're going to form again the phenoxide salt and H2. So in case of AS or O levels, when acid and metals react, it is going to form H2 gas, right? It is going to form hydrogen gas, and it is also going to form the salt. So from that idea only, we can understand this phenol structure is going to react with the metal, forming phenoxide, sodium phenoxide, and H2 gas. The reason we add or multiply with 2 is because we want to form H2 to balance both sides of the equation. Since one H atom that is not H atom, but H ion, hydrogen ion leaves the structure, we want two hydrogen ions to join together forming H2. Hence, we are going to add 2 over here to balance both sides of the equation. Fair enough, this is your acid plus metal reaction. Now let's talk about the third reaction of phenols, that is phenols reacting with diazonium salt. Previously, what you saw is diazonium salts forming, that is over here, or diazonium ions, that is there is an azo group and it is going to form an ion. This is your diazonium ion, and due to the existence of chloride ion, this is your diazonium salt. Now, what's going to happen is when you react a phenol with the diazonium salt, it is going to form an azo compound. That is a compound that has the azo group, that is N triple bonded to N. So we're going to see how it is going to take place. So in general, diazonium ions are very reactive since, as mentioned, these are unstable. So they carry this group N triple bonded to N. Why the positive charge? Since N has 4 bonds, so it has a partial positive charge. Because usually, as mentioned, 3 bonds and 1 lone pair. Now, when it has four bonds, it is going to give its electron to form the bond. So a partial positive charge. A positive charge. Now, in step 1, what's going to happen is to make the phenol more reactive, once again, we're going to form phenoxide ion. So obtain phenoxide ion, that is, we're going to react the phenol with NaOH forming salt, that is sodium phenoxide, along with water. Step 2, we're going to form the azo compound. This solution needs to be cooled in ice. Cold diazonium ions are added to it. So after the reaction, yellow-orange PPT precipitate is seen of an azo compound. Could be a yellow solution as well. Now, this is your diazonium ion, right? This is your diazonium ion and this is your phenoxide ion, right? Due to the higher negative charge, it is now more prone for a reaction to take place. Great. Now, what's going to happen is this azo group, very simply, this azo group will attach to this position. Just remember, it is going to attach to the furthest position, or 1, 2, 3, 4, fourth position in general, until and unless you have other groups attached. But in these conditions, what's going to happen is you're going to occupy the 4th position exactly parallel to the OH group. That is what you're going to see in most azo compounds, right? So as the phenoxide ion, due to the higher negative charge, more reactive now, is going to react with this benzene diazonium ion, and what it's going to do is it's going to turn into a more stable product. How, you ask? This triple bond is no longer there. This is going to now form N double bonded to N, each of these bonded to a benzene structure. Hence, this is far more stable. And this double bond acts as a bridge. And how that is going to help is that this ring structure and this ring structure, there are electrons in both, right? There are delocalized electrons in both ring structure. Now, this compound is far more stable. Why, you ask? Because electrons from here can move on to here, electrons from here can move on to here due to this bridge, right? Now, this compound, due to a more spread out negative charge, is far more stable. And this is your nitrogen bridge. And the color of this is going to be yellow, and this is going to be yellow precipitate if the reaction takes place. And for the conditions, it needs to be cooled, that is less than 10 degrees Celsius, definitely, and you're going to add ice to the reaction for the reaction to take place, right? Fair enough. So, in short, to remember this, in general, when working with producing diazonium salts, you're going to need cold conditions, ice, But when you're going to form phenols, only then you'll heat the structure, that is the diazonium chloride ion. So only when you want to produce the phenol, only then you're going to heat the structure. Otherwise, mostly when working with diazonium ions, you're going to require cold conditions for reactions to take place, such as producing azonium, azo compound. Anyways, so in this reaction, we saw how phenoxide ion is going to react with benzene diazonium ion and is going to form an azo compound. Okay. Now, the fourth and fifth part, that is, what is the fifth part? Bromination, right? So fourth and fifth part, electrophilic substitution reaction. The only difference over here compared to your previous topic, that was Arenes. Compared to that, the only difference is you have a group attached to it, that is OH group, which is why there's going to be a directing effect. Now, nitration and bromination are electrophilic substitution reaction. Phenols are more reactive than benzene due to OH, right? Which has a lone pair of electrons overlapping with the electron ring, and it donates electrons into the ring structure. You know it very well by now. So this makes the electron more dense with electrons. This makes the ring more dense with electrons. Hence, it is more susceptible to electrophilic substitution reaction. As mentioned, OH group attached to the benzene structure. This activates certain groups, specifically 2, 4, and 6. Hence, makes this highly dense with electrons. Hence, electrophilic substitution is more prone to take place. Okay. Now, in case of nitration, to carry out nitration, you're going to simply add dilute nitric acid in room temperature, and it is going to produce a mixture of 2-nitrophenol and 4-nitrophenol, because it activates both positions, which is why both are going to happen as a mixture. Now, in case of dilute HNO3, you're going to get either this or this. So either 2-nitrophenol or 4-nitrophenol, either of the two. Now, the moment you add concentrated or higher concentration of NO3 ions, in that case, even in room temperature, it is going to produce 2,4,6 trinitrophenol. That is, all three activated positions are going to be occupied by NO2, right? So nitration is going to take place. So it forms 2,4,6 trinitrophenol and 3 water molecules, right? Due to the H being replaced, right? Due to the H being replaced. Fair enough. Now, you know that when dilute, what was I saying? Yeah, when you add dilute nitric acid, only one substitution takes place. When you have concentrated nitric acid, all three positions will go through substitution. That's the only thing. And this reaction takes place at room temperature. Nothing else for nitration. Now, for bromination, what are you going to do? You're going to add phenol to bromine water, that is aqueous bromine. So that is going to allow for electrophilic substitution to take place at room temperature. Again, this is also going to take place at room temperature. So not too many temperatures to remember, luckily. Okay, now what's going to happen is, bromine has orange color. So when the reaction goes to completion, you're going to see the orange color decolorizes and it's going to be a transparent solution. So this bromine bond is going to break and it's going to form 2,4,6 tribromophenol. That is, all three positions of the carbon atoms that is activated is going to go through substitution reaction. That is, the H plus is going to be replaced by Br plus. And the other Br minus ions are going to react with H plus, forming 3HBr. And this reaction takes place at room temperature, and you know that aqueous bromine is orange in color. Decolorizes, the reaction is taking place. Now the last thing, semi-last thing, is acidity and relative acidity of phenols. Now, quickly, I don't want to spend too much time on this because it's fairly easy and I want to focus on reactions mostly. But acidity of phenols. Phenols act like alcohol due to the OH group, so they are weakly acidic, right? Lone pair of electrons from the oxygen joins the delocalized electron ring, that is OH over here, and your phenol structure, electrons join the benzene ring. Now, this gives the acidic nature as O is no longer highly negative. O does not have a high negative charge, which is why it is not going to pull back the H plus ion. That is, if dissociated, this H plus ion is less likely to be pulled back by this oxygen, partially negative oxygen atom. Since the oxygen lost its electron to the benzene structure, it is less likely to attract the H plus ions. So it is a better acid compared to ethanol, let's say. Since in ethanol, you have CH3, CH2, OH, and in this case, there is electron donating group and the oxygen atom has a highly negative charge, right? Hence, it is more prone to pull back the H plus ion. Hence, this is a worse acid. Why? Because it is not going to dissociate. It is not going to have a higher concentration of H plus ions in the solution. Whereas in case of phenols, when it loses the H plus, it is less likely to pull back the H plus, since the charge of the negative charge of the oxygen is distributed through the benzene structure. So that is what I talk about. And once this H plus is lost, the phenol becomes a conjugate base. That is, it is going to act as a base, since it has the ability to attract back H plus now. This negative charge is spread over the ion through the benzene structure. Since the oxygen atom is not as electronegative, it can't pull back the H plus strongly. Phenols are more acidic compared to ethanols. It is more acidic. Now, phenols are more acidic than basic, more likely to lose H plus ions. That is, for having the ability to be basic, that basically means that you need to be able to pull back the H plus ions. But as we saw, the oxygen loses or distributes its negative charge through the benzene structure. So its ability to lose the H plus is far more or far greater than its ability to pull back the H plus. That is its basic nature, which is why it is a better acid than base. Now, how stable is the phenoxide ion? Phenols ionize and become phenoxide, which is more stable due to the charge density being spread out, right? So due to that charge, even though it turns into an ion, but compared to other cases, other compounds, this charge is not going to be dense on the oxygen atom. It is going to be distributed through the benzene structure, which is why this ion is far more stable. So phenols are more likely to be ionized. So the equilibrium lies to the right side, that is, of losing the H plus. It is more prone to lose the electrons. Notice a larger arrow, forward reaction, backward reaction, smaller arrow, denoting forward reaction is far more prone. So if you find the Ka, it will be large. That is equilibrium constant. Fair enough. So it is more acidic than basic. So in short, if you look at this table, this is showing how acidic compounds are compared to others. Phenols, more acidic than water, which is more acidic than ethanol. In short, if I say, phenols are more acidic than ethanol. CH3, CH2, OH, electron donating effect, which is why it is less likely to lose this H plus, and it is going to pull back the H plus. In case of phenols, notice one thing. Due to the negative charge being distributed to the benzene structure, it is less likely to pull back the H plus. However, in case of water, OH, this is the hydroxide ion. Once the H plus is lost, now it does somewhat have the ability to pull back the H plus. So it is a weaker acid compared to phenols. However, it is a stronger acid compared to ethanol. Why you ask? Because in case of ethanol, there is OH. Here is also OH. However, in case of ethanol, there is electron donating group. In case of water, there is no electron donating group, which is why it is a better acid than ethanol, but a worse acid compared to phenol. So try to understand that very carefully, because questions about relative acidity or basicity is going to come quite often in the paper. That is, in short, what's going to happen. So phenol is a better acid compared to water, which is a better acid compared to ethanol. Last thing is naphthol for this section, that is hydroxy compounds. So the last thing we talk about is that, notice this is similar to hydroxy compounds, and it is also going to react similar to your phenols. So it basically, this phenol, one of the phenol is attached to a benzene structure, and this is called 1-naphthol. So it is chemically going to react similar to phenols. So electrophilic substitution, if it was to take place, it would take place in 2 and 4 position. Why you ask? Because in case of phenols, what do you see? It activates 2, 4, 6 position. Now over here, 6th position is occupied by a carbon-carbon bond with the next adjacent benzene structure, which is why over here no electrophilic substitution takes place. So in case of naphthols, electrophilic substitution reaction does take place just like hydroxide, but in 2, 4 position. So yeah, that's it for this this section. And next section, which is carboxylic acids and its derivative, then nitrogen compounds. So see you in the next one. So now in this section, we're going to study about carboxylic acid and their derivatives. So first up, we will talk about how to produce benzoic acid. That is, how to produce a carboxylic acid. So you know from the first section already, talking about hydrocarbons in general and arenes and benzene structure. From there, you know, if an alkyl group is attached to the benzene structure, what happens? It is going to be oxidized into COOH. So exactly the same thing we're going to talk about over here in short. So what are we going to do? We're going to oxidize the alkylbenzene. So alkanes in general do not go for oxidation, even if you add a strong oxidizing agent. However, in our case, it is added or attached to a benzene structure, which is why this reaction takes place. Now, for this reaction to take place, what are we going to do? We're going to reflux this mixture, this organic compound, that is alkylbenzene, with what? Alkaline KMnO4, right? We're going to reflux with alkaline KMnO4, that is potassium manganate, and it is going to be hot. So reflux with hot alkaline KMnO4, and after that reaction is taking place with your solution, what you're going to do is you're going to acidify that solution with what? Dilute acid, H2SO4, right? Now, your question might be, why do we need to acidify the resulting solution? So let me tell you. This methyl benzene, the moment you oxidize, reflux with alkaline, notice, alkaline KMnO4, potassium manganate, what's going to happen is this H+, the H+ that was supposed to be over here, COOH, would be replaced with K, that is potassium, due to the alkaline condition. So at the end of this reaction, what you would be left with is potassium benzoate, a salt, right? You would be left with a salt. Now, we don't want a salt. What do we want? We want benzoic acid. That is over here, benzoic acid. We are producing benzoic acid. So to make sure at the end we're left with benzoic acid, we're going to further acidify this solution. That is, we're going to protonate the solution. That is, we're going to add H+, right? When you add H2SO4 or any other acid, let's say hydrochloric acid, you're adding a concentration of H+ ions into the solution, which is why you're going to replace this salt, that is this metal ion, with H+. And at the end of the day, you'll be left with COOH. So other than this, I've just broken down the bond and displayed the bond over here. You can just write it as COOH. Does not matter. Fair enough. So that is how to produce benzoic acid. Now, if you were asked what would be the observation in this reaction, you can simply say, since you know potassium manganate is purple in color before being oxidized, after this potassium manganate gets reduced, that is, it oxidizes the methyl benzene, what's going to happen is there would be brown PPT of manganate ion. That is, this Mn4+, this got reduced from Mn7+. It itself got reduced by oxidizing another species, that is methyl benzene again. So since it got reduced, it's going to form brown PPT of MnO2, manganese oxide, right? Fair enough. So due to this reduction taking place of our oxidizing agent, you're going to see a purple solution turning into brown PPT, right? That's going to be your observation. Now again, one more thing, whatever alkyl group is attached, that is propyl group, ethyl group, butyl group, doesn't matter, everything is going to turn into COOH, nothing more, nothing less. It's not going to be any other acid other than benzoic acid. Fair enough. Now for the next part, we're going to talk about how to produce acyl chlorides. That is, acyl chlorides in general, you know, they're going to be like an R group attached to C double bonded to O and a Cl, that is halide. Now this, due to this halide ion, that is Cl minus being attached to this electrophile C plus, they form acyl chloride. Now acyls can be literally anything. Now in our case, we are working with acyl chloride. Now the main functional group of acyls are this C double bond O group. This is the main functional group of acyls in general. Now when you're going to be talking about acyl chloride, it's going to be R bonded to C, double bonded to oxygen atom, and this carbon atom also bonded to chlorine atom. Fair enough. Now what we're going to do is we're going to form this acyl chloride, which you saw C double bonded to O. We're going to form this from what? From carboxylic acid. That is what we're going to do over here. How to form acyl chlorides. Now, you know what acyl chlorides look like? This is a typical example of ethanol fluoride, right? Now, if you added one more CH2 over here in the middle, what would happen? You would form propanol chloride. Fair enough. So that's how we name the acyl chlorides. Fair enough. Now, these tend to be more reactive compared to carboxylic acid. Now take a wild guess why they are more reactive. Due to this C double bonded to O plus this halogen as well, both of which are highly electronegative. For one thing, this oxygen atom, due to double bond, is pulling electrons away. The other thing is this chlorine atom is also very electronegative, which is why it wants to pull the electrons away from it, right? Fair enough. So we have two electronegative atoms attached to our C bond, right? To our C atom, sorry. So these tend to be far more reactive compared to carboxylic acids, which is why they are often used rather than carboxylic acid for organic synthesis such as ester production. In ester production, what do you know? C double bonded to O, OH plus OH, that is of alcohol, right? Now what happens in producing an ester is this is going to produce water and you're going to have ester linkage. Now what we understand is carboxylic acids are very weak acids. The other thing is carboxylic acids are very less reactive compared to ethanol or acyl chlorides. The reason for that is acyl chlorides tend to be more reactive due to two electronegative atoms attached to the carbon group. Hence, we prefer working with acyl chlorides, right? We prefer working with acyl chlorides such that we can easily produce esters, right? It is easier to produce esters. But also keep in mind that acyl chlorides in general are more expensive to work with, which is why in industry they might be willing to work with carboxylic acid even though it is weaker, right? In acyl chlorides, notice the carbon is next to two electron withdrawing groups, the O double bond and Cl, which is why it has its electrons drawn away by two highly electronegative atoms. This makes the carbon and carbon atom much more electrophilic. That is more positive. More what? More positive. Hence, carbonyls are more reactive than carboxylic acids. So, this is why we want to produce acyls. That is acyl chloride. Okay, now how to produce acyl chloride? Acyl chlorides can be prepared by reacting carboxylic acid with three sorts of reagents. This part, mind you, very important. A lot of questions are going to come from this section. Not directly, but in a step, you will be asked to remember this. Answer this. So, there are three ways to produce. That is the fun part. Now, how do you produce acyl chloride? First thing you're going to do is you're going to take your typical carboxylic acid. What are you going to take? In our case, I'm taking what? Ethanoic acid. I'm taking ethanoic acid, right? Ethanoic acid. I don't know why I didn't name them. But anyways, so you're working with ethanoic acid and you're also going to bring a halogen carrier. Since we're going to produce which halogen? Acyl chloride, right? So we're working with chlorides, which is why we are bringing chlorine carrier in this case. That is PCl₅, right? PCl₅. This is carrying our chlorine atoms. So we are going to react PCl₅ with what? Carboxylic acid. Now, what's going to happen is when we react both of these at room temperature, you're going to produce ethanol chloride, that is our acyl chloride, and HCl and POCl3. Now, why are these forming? Let's understand. So, now when you have ethanoic acid reacting with PCl₅, notice one thing. For ethanol chloride, what I want is the OH part to be eradicated from the molecule structure. I want the OH molecule, OH part or the OH ion to leave the entire molecule structure, right? Fair enough. So I want these two to leave. Now, when these two are going to leave, what's going to happen is this H and this Cl are going to form a bond. These two will form what? Take a wild guess. HCl. So the H leaves and is going to form HCl. So we have accounted for the existence of those two. Now we also have four other chlorine atoms. What are we going to do with those? Let's see. This chlorine group or chlorine atom or any of these four chlorine atoms are going to do something very simple. What are they going to do? They are going to replace this oxygen atom. Fair enough. So one of the four chlorine atoms are now going to replace the oxygen atom. Now where will this oxygen atom go? Let's see. This oxygen atom will join PCl3. This oxygen atom is going to join PCl3. Now, this part is the next thing I'm going to say is not needed for you, but just to make you understand is, notice one thing. Two electronegative atoms are leaving. That is Cl minus, Cl minus. Two Cl minus are leaving the structure. This and this. Right? Which is why oxygen is coming in, whose charge tends to be O2 minus. So they're going to fulfill the place of the two Cl minus ions, the two halide ions, that is chloride ions, which is why the O is going to join PCl3. They're going to join PCl3 and form what? And going to form, wait a minute, POCl3. this is how the reaction is taking place. So the H is going to leave and is going to form hydrochloric acid. The O is going to leave and form a bond with PCl3 forming POCl3. And you're going to be left with your ideal ethanol chloride, right? Fair enough. So this is how the reaction is taking place at room temperature. No other conditions are needed. PCl₅ is very reactive, which is why no other reagents or catalysts are needed. Fair enough. So that is one way of producing your ethanol chloride. The next way is using PCl3. We're going to now use PCl3. I guess it's phosphoric tetrachloride or something like that. I forgot the name. But anyways, we're going to use PCl3. What are we going to do over here is this PCl3 is going to react with three molecules of carboxylic acid. Carboxylic acid. 3 molecules. Very necessary over here. Why? Let's see. Because all of these Cl atoms are going to replace the OH. The OH part of the molecules, right? So the Cl atoms are going to replace the OH ions, right? Fair enough. So the Cl ions, halide ions, Cl minus are going to replace OH ions, which is why the OH minus ions are going to form a bond with your phosphorus. Are going to form a bond with the remaining phosphorus. Since the chlorine atoms, or actually chloride ions, are going to take up the place of OH ions, in that case, the OH has to go somewhere and the phosphorus is left alone. So the phosphorus left alone is going to join with the 3 hydroxide ions. And what do they form? They very interestingly are going to form H3PO3. Can you remember what this is? This is basically phosphoric acid, right? It's going to form phosphoric acid. Fair enough. So what did we understand from this part? 3 molecules of ethanoic acid or any sort of acid is going to react with PCl3. In return, it's going to form 3 molecules of, in our case, ethanol chloride. And also form H3PO3, right? That is phosphoric acid. Fair enough. And this reaction is also going to take place at room temperature. Why? PCl3 is very reactive. Last way to do it is using SOCl, right? Now, using SOCl, notice the bond structure over here. It's going to react with 1 molecule of ethanoic acid. And this reaction needs heat because SOCl is not going to readily react with your ethanoic acid or carboxylic acid. Fair enough. Now, what's going to happen over here is you're going to form 2 byproducts over here. SO2, sulfur dioxide, and HCl, right? Sulfur dioxide and HCl. Now, what happens is the two Cl atoms, one is going to replace the OH minus ion, that is hydroxide ion, and the other is going to form a bond with the H. So one is going to form a bond with the H, the other is going to replace the O ion, that is O2 minus ion, and then 2 minus. And this oxide ion is going to do what? Is going to form a bond with the remaining S. Is going to form a bond with the sulfur. Now, this sulfur is going to form sulfur dioxide. This is going to form sulfur dioxide, right? Fair enough. So you get what? You get sulfur dioxide, you get HCl, and you get ethanoic acid, right? Fair enough. So this is how you can produce ethanol chloride in 3 ways. So one way, from ethanoic acid, react with PCl₅, produce ethanol chloride, HCl, and POCl3. The other way is 3 molecules of ethanoic acid react with 1 molecule of PCl3 at room temperatures, it's going to produce 3 molecules of ethanol chloride and 1 molecule of phosphoric acid according to molar ratio. Now, the other way is reacting ethanoic acid with SOCl. It's SOCl2, sorry. Yeah, SOCl2. So one molecule of ethanoic acid reacts with SOCl2 and is going to form what? It's going to form ethanol chloride, and also going to form HCl and sulfur dioxide. So remember the products, remember the condition. Just remember, in case of using SOCl2, in that case only you're going to require heat. Fair enough. So that is the second part, right? Third part, let's quickly move over. We're going to talk about further oxidation of carboxylic acid. Now, in general, from AS, what do you know? From AS, you know that carboxylic acids in general do not further oxidize. Why do you know that? Because from alcohols that you studied in AS, that is turning an alcohol into what you call it, aldehyde or ketone. And in case of ketone, they don't further oxidify, but oxidize, sorry. Yeah, so ketones don't further oxidize. However, aldehydes do oxidize. Aldehydes are going to turn into what? Aldehydes are going to turn into carboxylic acid. In case of alcohol, they can either go the ketone route, that is, if they have 2 R groups attached, they form ketone. And in case of alcohol, where there is 1 H group and 1 R group, in that case, they're going to form aldehydes. Fair enough. So there are 2 routes to be taken. However, in AS, we learned carboxylic acids don't further oxidize. Now we are going to learn 2 exceptions. One of the exception you probably already know of, that is methanoic acid being able to be oxidized. The other exception is ethane dioic acid. This is the other exception where your, what you call it, carboxylic acid does get oxidized. So we're going to talk about both of these exceptions that goes through further oxidation. Now, this is what I'm talking about, that in AS, what you learned about primary alcohols, that is, primary alcohols that is attached to 1 H group, 1 R group, and 1 H group again. This is going to go through 3 stages. First, turn into aldehyde. And then this aldehyde is going to be further oxidized. That is 1 R group and 1 H group. This is going to be further oxidized into carboxylic acid. Now, turning from aldehydes to carboxylic acid, you can go for 3 things. One is potassium chromate, the other is potassium manganate. And these 2, which you learned in AS, is Tollens reagent and Felling's solution. Felling's solution will give you most likely, brick red PPT, that is red PPT. And in case of Tollens reagent, it's going to form silver layer, that is Ag plus is going to get reduced, right? Yeah, Ag plus, that is silver ions, are going to be reduced. So, there are 4 ways to oxidize your aldehyde. These 2 are arguably weaker ways, and these are strong oxidizing agents, that is potassium chromate and potassium manganate. Now, in case of turning primary alcohol into aldehyde, you need strong oxidizing agent, right? And turning aldehyde into carboxylic acid, you can use these 2 reagents as well. Fair enough. Now, the other thing was, that was secondary, I guess. So, if you have 2 R groups attached, that is going to be, this is going to oxidize into a ketone, right? If you oxidize this using these reagents, it's going to form a ketone. 2 R groups attached. What's going to happen is, if you have 2 R groups attached, it's going to form a ketone. If 1 R group attached, you're going to form an aldehyde, and then from aldehyde to carboxylic acid. The reason I'm talking about this again, although it's from AS, you will require certain bits of information from the AS level as well. So I'm going over this again, once again, but this is not the main part of this section. The main part is knowing carboxylic acids don't go through further oxidation. Therefore, talking about the two exceptions, it's going to be methanoic acid. It's going to be methanoic acid and ethane dioic acid. Fair enough. So methanoic acid, what's going to happen is, notice one thing. Now, you don't need to know this again. I'm giving you additional information. This methanoic acid, the reason it's going to go through oxidation is because of this aldehyde group. So this basically acts as the aldehyde group, because in general, you know, aldehydes are like this. Right? You know, aldehydes are going to have one H group, one R group, and double bonded to oxygen atom. Yeah, exactly like that. So what happens is, this portion of the molecule is going to act like an aldehyde, which is why this will easily be oxidized. Now, not into a carboxylic acid, rather into carbon dioxide, right? It's going to be oxidized into carbon dioxide. So this oxidation does not require a strong oxidizing agent. You can use mild oxidizing agent. This is also why I reviewed this part. That is to know what are the mild oxidizing agent. They're going to be Fehling solution, or it's going to be Tollens-free agent. So you can use mild oxidizing agent, and it is going to form carbon dioxide. And in case of Fehling solution, what happens is Cu2 plus is going to be reduced. So Cu2 plus is going to be reduced and is going to oxidize this. So it itself is going to be reduced, forming red PBT. Okay. And if you use Tollens reagent, you know, from this silver ion, it's going to be what? Reduced. And it's going to form silver. Right? You see a layer of silver on the solution. And that is going to tell you that oxidation has taken place. Right? Fair enough. So that is one way, mild oxidizing agent. The other way is strong oxidizing agent. That is KMnO4 and potassium chromate. In case of potassium manganate, you're going to use acidified potassium manganate. What is that going to do? That is going to turn from a purple solution to colorless. From purple solution to colorless. That is Mn7 plus to Mn2 plus. In previous case, in one of the section, I don't remember which one. I guess this one. Yeah. So in this case, what happens is this reduces to Mn4 plus, which is why you see brown PBT. Now, in this case, since it's reacting with the acid and is in acidified condition, what's going to happen is it gets further reduced to the state of Mn2 plus. Now, this is why the solution goes from purple to colorless. Okay, fair enough. Now, the moment you add acidified potassium chromate, what's going to happen? It is going to go from orange to green, right? This is your AS level orange. That is turning from Cr6 plus, that is chromium 6 plus ion, turning to chromium 3 plus ion. That is why from orange to green solution. Now that is the case of methanoic acid, that is turning into CO2. Fair enough. The other case let's talk about is ethane dioic acid. This is also going to be oxidized by what? Any strong oxidizing agent you take is going to be oxidized. In this case, this is harder to oxidize, which is why you're going to use a stronger oxidizing agent, of course. In that case, you can use hot acidified potassium manganate, right? So hot acidified potassium manganate, it is going to do the same thing. In case of ethane dioic acid, it is going to oxidize this into CO2, and to account for the 2OH, it is going to form 2H2O, right? It is going to form 2 water molecules and 2 carbon dioxide molecules. Fair enough. So that is how you're going to oxidize certain carboxylic acid, that is, in our case, methanoic acid and ethane dioic acid. The 2 exceptions where the carboxylic acid goes through further oxidation. Fair enough. Now, for the 4th part, we're going to talk about the relative acidity of carboxylic acids and phenols. Which one is the stronger acid, right? Now, I'm going to talk about this in short. But the main idea is, if the carbon atom has a higher negative charge, right? It has a higher negative charge due to electron donating groups. Attached in that case. If this has a higher negative charge, or a lower positive charge, however you want to say it, in that case, it becomes easier to gain back the H plus ion. Because understand it logically, if your negative charge on this carbon atom is higher, I mean, the carbon atom is not going to have a negative charge, but it's going to have a positive charge, logically, because it's going to form a carboxylate ion. So let's talk about it more accurately. So if this carbon atom has a lower positive charge, much lower positive charge, it becomes easier to gain back this H plus ion, However, if you had one other carbon atom which had a higher positive charge, a much higher positive charge, in that case, it wouldn't gain back the H plus ion because repulsion, right? It is not going to gain back the H plus ion, which is why if you have more electron withdrawing group, that is C double bond O bonded to O, in this case, notice, stronger electron withdrawing group, which is why it's going to find a hard time to gain back this lost H plus ion, which is why carboxylic acid, in case of carboxylic acid, it is a stronger acid because the hydrogen ion concentration in the solution is much more, because it is not gained back by the carboxylate ion, that is this ion. It is not gained back by the carboxylate ion, right? Which is why it's a stronger acid. Now, in case of phenols, what happens is, yes, even in phenols, this oxygen atom is actually going to lose its electron to the ring structure. It's going to lose its electron to the ring structure, okay? Now, what's going to happen is, in this case, this oxygen atom will not have a large negative charge. It will have a low or less negative charge, which is why it is indeed hard to gain back the H plus ion. It is what? It is hard to gain back the H plus ion, right? It is hard to gain back the H plus ion. However, notice one thing. Since this oxygen atom is losing its electron to the ring structure, this carboxylate ion, that is C positive ion, carbon positive ion, is actually less stable. Why? Because notice, this oxygen atom is losing its electron to what? To this ring structure. Hence, the negative charge of this oxygen atom has been distributed within the carbon ring. So, the positive charge on this carbon ion has decreased. Has what? Decreased. Which is why this has a easier or a higher probability of gaining back the H plus ion. In case of carboxylic acid, notice, since this oxygen atom double bonded to the carbon atom is a stronger electron withdrawing group due to the double bond, it forms a more stable carboxylate ion, that is C plus ion, C positive ion, which is why it does not gain back the hydrogen ion. Since the ion form, the carboxylate ion form, is much more stable compared to the phenol. Because over here, the C plus ion is no longer that positive due to the oxygen atom losing its electrons to what? To the ring structure. And inside the ring structure, that negative charge has been spread over. So the positive charge on the carbon atom has decreased, which is why this is a weaker acid compared to what? Compared to carboxylic acid. Another example let me give. If there was CH2, CH3 attached, that is propanoic acid, ethanoic acid, what's going to happen in that case? This is electron donating group, right? It's going to donate electrons to this carbon positive ion. In that case, the positive charge on the carbon atom decreases. Does what? Decreases, right? Which is why this is going to have an easier time gaining back this hydrogen ion, right? It's going to have an easier time gaining back the hydrogen ion, which is why it is what? A weaker acid compared to methanoic acid or ethanoic acid. Since in ethanoic acid's case or methanoic acid's case, what happens? The positive charge on the carbon atom is larger. Hence, it is less likely to gain back the H plus ion. Hence, the H plus concentration in the solution increases. So you can read this out for yourself if you want to understand better, but that is all about relative acidity. It's all about how many electrons there are on the carbon atom, electron donating group and electron withdrawing group, right? How stable the C plus, the carboxylate ion is going to be. So if you keep that in mind, you'll be able to answer the question about relative acidity. Moving on, we're now going to talk about production of esters from acyl chlorides. So, part 5, you know how to form esters in general. Carboxylic acid, any sort of alcohol react, forms water molecule, condensation reaction, and you're going to get your ester. Now, towards the beginning of this video, I told that the reason we need acyl chloride is because acyl chlorides are much more reactive, right? Acyl chlorides are much more reactive. So now we are going to see how to form esters from what? Acyl chlorides. So we're going to react acyl chloride with alcohols to form esters. Esters in general have this functional group, this C double bonded 2O attached to another oxygen atom. If you see this is ester linkage. Since acyl chlorides are more reactive, we are going to react with acyl chloride with alcohol. Now, in case of acyl chlorides, the reaction goes to completion and the reaction is faster. We get higher yield of the ester. Now, we are going to look at 3 cases to form the esters. First case, we are going to react ethanol chloride, very well-known molecule, with ethanol, right? Ethanol chloride with ethanol. It's going to form ethyl ethanoate, the alcohol name first, and the carboxylic acid at the end. Fair enough. So now, let's do one thing. We are going to react ethanol chloride over here and ethanol over here. What's going to happen is pretty much the same thing. This H is going to bond with the Cl ion. H plus bonds with Cl minus ion and forms what? Forms HCl. Forms HCl. And you're also going to form ethyl ethanoate. That is this ester, the main icon of this reaction. So what happens is, as these two form HCl, the rest of the molecules are joining together, forming this ester linkage and forming this ester. Great. Now part B. In part A, we saw how to form ester from ethanol chloride and ethanol. Now we are going to see how to form ester from benzoyl chloride and phenol, right? We're going to form our phenyl benzoate, that is our ester, phenyl benzoate, that is from 2 phenolic structure, we are going to form our ester. So we have our acyl chloride, that is benzoyl chloride, and we have our alcohol. Both of these we are going to react. Same thing is going to take place. Cl atom, chloride ion is going to react with H plus ion and going to form HCl. Why NaCl? I'm going to talk about it due to this Na atom. But yeah, in general, in acidified condition, it would form HCl. Fair enough. and the rest of the molecule is going to join together. HCl is going to be is going to move out and is going to form C double bond O, O bond. This is your ester linkage. So all of these join together to form the ester linkage, and you can see over here how they form the ester linkage. Now, in this case, you need to follow a few conditions. Why you need to follow a few conditions? The thing is, reacting phenols are harder. Reacting phenols are harder. I explained this over here, I guess. So, reacting phenols are hardest due to the phenolic structure, due to the benzene structure, because they are more stable, right? So, you need to add other reagents, that is, you need to heat the mixture, and we use NaOH. The reason we use NaOH is basically we're substituting of, you know this from the phenol section of this video, that the moment the H plus ion is replaced by the sodium ion, it is a far better reagent. It is a far better reactant. It is more prone to react with the other reagent, in this case benzoyl chloride, right? So we're replacing this H plus. We're replacing what? We're replacing the H plus with Na, such that the reaction is faster and more effective. That's the point of using NaOH and heating, because as I told you, they're more stable, so we need heat to carry out the reaction. Great. If you understand that, you know how the ester is forming and why we get NaCl instead of HCl, right? Since this is going to now react with the Cl ion and is going to form a solution of NaCl salt. Right. Now, a lot of the things I'm going to mention is for the sake of explaining it, not exactly because it's in directly in your syllabus or it's going to come in your paper, but because it's better to understand it such that you understand why the reaction is taking place, and it makes it easier to memorize the reagents and conditions, right? So now in the next case, 5C, what we see. Okay, so in this case, we're going to react ethanol chloride with phenol, right? Ethanol chloride with phenol. We have already worked with ethanol chloride, but we didn't work with it along with the phenol. Now again, in case of phenols, what happened is, since the phenols are more stable, in that case, it's going to require other reagents and other conditions. So even in this case, we're going to require NaOH and we're going to require heat, right? We're going to require NaOH, we're going to require heat. Why NaOH? Replaces H plus ion and forms NaO and this benzene structure, right? Fair enough. It forms a salt. Right, phenyl benzoate salt. So in this case also, we're adding heat because of this stable structure. Great. Same thing happens. HCl is going to react, forming HCl. However, it is going to turn into NaCl. Why is it going to turn into NaCl? The reason being this Na reacting with Cl. Hence forming what? Hence forming NaCl. Fair enough. And you also have your ethanol chloride joining with your phenoxide ion, that is O minus and benzene structure. So this reacts with this, forming what? This ester, right? Is going to form this ester. Fair enough. So okay, so the other thing is, I forgot to write H2O over here. There's going to be another byproduct, H2O, sorry. Since OH and this H is going to react, forming H2O. And yeah, this one is right. It forms NaCl and H2O. Where H2O comes from? Basically OH and H. Hence H2O. Fair enough. So that is how you're going to have a reaction between ethanol chloride and phenol, right? Both of these similar cases, since phenols are reacting these reagents, right? You remember one, you're going to remember the other. Fair enough. So in the phenol molecule is added by breaking the C double bond O addition reaction, and the Cl atom is eliminated, and that is the elimination part of the reaction, along with the H being eliminated. the C double bond O is then reformed. What on earth did I say over here? So let me explain. So in case of all of these reactions, notice one thing I probably mentioned somewhere. These are all at addition-elimination reaction. What are addition-elimination reaction? Notice one thing. In let me take this example. Let me take this example. Right. In this case, this phenol is going to do something very interesting. It's going to add itself. It's going to break this double bond. It's going to push and break this double bond and do what? It's going to break this bond and form this intermediate with the ethanol chloride. With the ethanol chloride. I'm going to talk about the mechanism, don't worry. So this phenol is going to attack this double bond, break the double bond, and it's going to force this Cl to remove itself from the molecule, along with this H plus being removed. How is this H plus removed, by the way? Because we added NaOH, right? So this Na is going to replace it either way, which makes it easier for this phenoxide ion to attack this C double bond O bond, which is why double bond breaks, single bond, and you form the intermediate. And then the Cl atom leaves the structure and it's going to form NaCl, and the H is going to bond with OH, forming H2. That is how you're forming the ester. So after the phenoxide ion attacks, breaks the double bond, and Cl atom leaves, the double bond is going to be created once again after this intermediate. Then again, this C double bond O will be reformed, right? So that it gets back to its stable state. When the double bond exists, the molecule is more stable. Hence, after the Cl atom leaves, it's going to reform the double bond. Fair enough. So that is in part what's happening in terms of the mechanism. So I'm going to show by drawing what the mechanism is going to be. This is what I explained. Okay, so in case of the mechanism, this is, again, remember, addition, elimination, reaction. Why addition? You're adding this phenoxide ion, the nucleophile, into the molecule by breaking the double bond. That is addition. Elimination, why? You're eliminating the chloride ion. That's why addition, elimination, reaction. You can also call this condensation reaction. Why? Because H2O is being formed. H2O is being formed. Right. So the mechanism is going to be what? We have this ethanol, what is this? Alcohol. So I've taken the example of alcohol, and you can also see this one. And this is from a question paper to see how it's going to be between two, one benzoic chloride and the other phenol, right? I talk about this in this one, benzoic chloride and phenol. So you can see this video, this question to understand how the mechanism is going to be. But let me explain the simple mechanism first. That is what? That is going to be, my friends, it's going to be ethanol chloride being attacked by this nucleophile. Why nucleophile? Lone pair of electrons. This is going to attack the partial positive carbon atom. Why partial positive? Mind you, O, electronegative, double bond, which is why it's going to pull the electrons away from the carbon atom. Cl is going to be electronegative, pulls electrons from the carbon atom, making the carbon atom highly positive and worthy of attacking because it's weak. So the nucleophile OH is going to find this chance and attack the carbon atom, right? The positive carbon atom. Hence, it's going to form this intermediate where? Notice one thing. It is going to form 4 bonds. This carbon atom is going to form 4 bonds. One with the oxygen, one with the Cl, one with the CH3, one with the alcohol. Now, in the first step, notice one thing. The double bond is going to break. The double bond breaks. So, the electron goes to the oxygen atom, giving it a partial negative charge. Right? And this nucleophile attacks the carbon atom. So addition takes place. Next step, in the intermediate, what happens is the partial negative oxygen atom wants to reform the double bond. Hence, it gives its lone pair of electrons to this carbon bond, forming the double bond. And the Cl atom is kicked out, hence takes its lone pair of electrons as Cl minus, so leaves as Cl minus chloride ion. And notice one thing, since this oxygen atom gave its lone pair of electrons to the positive carbon atom, it now has what? It now has a partial positive charge. So this hydrogen atom is going to sacrifice and give its lone pair of electrons, the bonding 2 electrons to the oxygen atom. Is going to give its bonding pair of electrons to the oxygen atom, both of them. And this H is going to leave as H plus ion. Great. It left as H plus ion, and it's going to now form the ester. And that H plus reacts with Cl minus, forming HCl. Now, if we look at another example of producing an ester, let's look at this one that is from the question paper. Here they're telling you that C6H5COCl is going to react with phenol, C6H5OH, to give the ester phenyl benzoate. An incomplete description of the mechanism of this reaction is shown. Draw the complete mechanism, right? So we have seen exactly this reaction take place above, that is forming phenyl benzoate. So over here, if you look at this one, this is phenyl benzoate, right? You have a phenyl structure that is a phenol reacting with benzoyl chloride, right? So this is going to form your phenyl benzoate, right? So we're going to now look at what the mechanism of this entire reaction is. Now, in the fifth process, we saw how to produce phenyl ethanoate, that is reacting ethanol chloride and phenol, forming phenyl ethanoate. This ethanoate name comes from this part, and phenyl due to the phenolic structure, right? That's why it's named phenyl ethanoate. Anyways, the main part, the mechanism of forming phenyl benzoate, we have benzoyl chloride reacting with our phenol. Now, this phenol is going to act as what? A nucleophile, since it has a lone pair of electrons. So this is going to target this carbon atom. Why? Because this has a partial positive charge. Partial what charge? Positive charge. Why? Because chlorine is going to attract the electrons, and due to the double bond over here and due to O being electronegative, it's going to pull the electrons away as well, hence leaving this carbon atom as very positive. Hence the nucleophile attacks this carbon atom with its lone pair of electrons, arrow over here, negative charge on the oxygen due to the partial negative charge, and carbon atom is going to have a partial positive charge. Fair enough. First box done. Next box, look at this. After the oxygen atom forms a bond with the carbon atom, that is oxygen of the phenol structure, it's going to now be partially positive. Why? Because it gave its lone pair of electrons and formed a dative bond with the carbon atom, the partially positive carbon atom. Fair enough. And in the previous case, you saw that the oxygen atom took its electrons away from this bond to help this phenolic structure attached to the carbon atom, right? So now this oxygen atom will have a lone pair of electrons. Hence, it will want to reform its double bond because this structure is not stable. So it will want to form the double bond again. But to do so, the carbon needs only 2 bonds, because if you have a double bond over here, you can only allow 2 more bonds. Hence, the Cl atom will now sacrifice and take its lone pair of electrons, that is electrons of this bond, and leave as chloride ion. Hence, take 2 electrons away from the structure. Now, what's going to happen? Chlorine goes away, taking 2 electrons. The oxygen atom gives back the 2 electrons, forming another, that is the double bond. And this hydrogen now, to fulfill the needs of this oxygen atom, that is the partial positive charge of the oxygen atom, this hydrogen is now going to give the lone pair of electrons, not the lone pair of electrons, but the bonding 2 electrons to the oxygen atom. To what? The oxygen atom. Hence, this H is going to leave as H plus, right? Fair enough. So this H plus is going to join the Cl minus and form what? And it's going to form HCl, right? And you'll see this double bond being reformed and these two bonds remain as it is, right? Fair enough. So this is your ester linkage, and this is your phenyl benzoate, right? So keep an eye on the mechanism, that is where the arrows are going, where the partial charges are going to be, where the lone pairs of electrons are. This is quite self-explanatory if you understand what's actually happening. This nucleophile attacks this partial positive carbon atom, and this double bond is broken, hence addition takes place, addition. And next what happens is this double bond reforms, this chlorine atom takes an exit, and to fulfill the needs of this positive oxygen atom, this hydrogen will also leave, right? So hydrogen and chlorine leaves, hence elimination, right? And at the end of the day, you have a stable structure where the double bond has reformed and you have the ester linkage. Fair enough. So over here, this is an addition elimination reaction. Now, the other thing to note over here is if this reaction was done in the presence of NaOH, that is alkaline conditions, this phenol, this H would have been replaced by Na, right? As seen with another example, if I'm not wrong. Yeah, these examples basically, where NaCl is formed, that is due to the fact this H being replaced by the Na, right? So if this was done in alkaline condition, rather than the H, you would have Na. And at the end of the day, you wouldn't have HCl, rather you would have NaCl. However, they have not mentioned alkaline condition, which is why you're writing your final product as HCl, right? Fair enough. Now that is basically it for production of ester. We can move on to the next part, which is going to be hydrolysis of acyl chloride, the sixth part of this unit. So hydrolysis of acyl chloride, this is again an addition-elimination reaction. Now, what are we going to add over here? Hydrolysis. So we're going to add the water molecule over here. So this acyl chloride is going to react with water. That is, we're adding the water molecule, where the water molecule is going to act as a nucleophile. How, you ask? Because notice, if this is your typical water molecule, right? And this oxygen atom is going to actually have a lone pair of electrons, actually two lone pairs of electrons. But yeah, it's going to act as a nucleophile and attack the structure. And at the end of the day, after hydrolysis has taken place, you'll be left with a carboxylic acid and HCl as your byproduct. Now, the H2 molecules added by breaking the C double bond O, C double bond with O, is going to be your addition part of the reaction, as mentioned. The O is going to act, the oxygen atom is going to act as a nucleophile, hence enters the molecule and breaks the double bond of C double bond O. And that is your addition part of the reaction, and the Cl and hydrogen atom being eliminated is going to be your elimination part of the reaction. And again, this C double bond O is going to reform as seen with previous cases. So what you have over here is this is your ethanol chloride reacting with H2O, and at the end of the day, this Cl and one of the H is going to leave as HCl, and the OH, the leaving the rest of the OH is going to react, or I mean displace this Cl atom, and is going to form ethanoic acid, right? This is your ethanoic acid. Ethanoic acid. Fair enough. So that is roughly what happens, but to see the mechanism, you'll understand better what's going to happen. That is, you have your ethanol chloride. You have your ethanol chloride reacting with H2O. Again, as mentioned, this oxygen atom is going to have a lone pair of electron, which is going to act as a nucleophile. So it wants to give its electron. It's going to find this partial positive carbon atom and hit this carbon atom and form a bond, right? It's going to form a bond. Now, to allow this oxygen atom is going to now take back its bonding 2 electron and is going to have a negative charge, right? Now, already it has a partial negative charge. Why I say partial? Because it is very electronegative. Hence, it pulls electrons away from the carbon atom, which is why it has a partial negative charge, and carbon atom is a partial positive charge. So, nucleophile hits, this double bond breaks. This oxygen now, after the addition has taken place, oxygen will have a lone pair of electron. And a negative charge, and will be ready to reform this double bond. However, while all that happens, this chlorine atom has to leave the structure for the double bond to reform, so it eliminates as Cl-. Now notice, since this bond was formed, this oxygen atom gave its 2 electrons into the bond, into the CO bond. Hence, this oxygen atom now has a partial positive charge, and this hydrogen atom now will have to sacrifice and give its 2 electrons or 2 bonding electrons to the oxygen atom, satisfying its needs. So this positive charge will now move away. Why? Because hydrogen atom has given its bonding electrons to the oxygen atom, positive oxygen atom. So at the end of the day, you have your OH bond. This H leaves and forms a bond with the Cl, and you have your double bond reformed, that is this one, right? So at the end of the day, what you have is ethanoic acid, not propanoic acid. Why did I write propanoic acid? I don't know. This is going to be ethanoic acid. So yeah, at the end of the day, you form ethanoic acid after reaction between ethanol chloride and water molecule. This is known as hydrolysis, where your nucleophile is going to be one water molecule. Fair enough. That is hydrolysis of acyl chloride. Next, moving on, we have the 7th part, which is going to be formation of amides. Now, you will also learn about this in the nitrogen compound chapter, but I'm not going to repeat this in the next chapter, so I'm going to cover it all in this one. So for the formation of amides, it's pretty simple. You form it from any sort of acyl chloride and ammonia or amines. So this is again another addition-elimination reaction as seen above. So you're going to add nucleophile, double bond breaks, you're going to eliminate certain atoms, and the double bond is going to reform. So it is another typical example of addition-elimination reaction. This is also a condensation reaction where the reaction between amine or ammonia is going to take place with acyl chloride. Why condensation reaction? Because there's going to be a byproduct which is going to be either HCl, H2O or anything, right? In our case, we have HCl. In previous case, we had HCl as well. This is also a condensation reaction. That is this one. Condensation reaction again, and where water molecule is formed, condensation reaction again, right? These are all examples of condensation reaction. This as well. So all of these are condensation reaction where, let's say amide linkages form or ester linkages form. There's going to be a byproduct, let's say HCl or H2O. So these are all condensation reaction. So sometimes you can answer the question of is this ester formation reaction a type of addition-elimination reaction or condensation reaction? You can write both, right? What type of reaction is it? Addition-elimination or condensation? Fair enough. So now, formation of amides. Let's see for a few examples how we can form the amide, right? First one, we're going to take ethanol chloride and react it with ammonia. Okay, so we're going to take ethanol chloride, react with ammonia. There is no other group attached. These are all H, that is hydrogen atoms. In case of amines, you will have other groups attached. Okay, so we're going to look for all of those examples, primary amine, secondary amine, and ammonia. Fair enough. So in case of reacting ethanol chloride with ammonia, what's going to happen is when you react, both of these atoms are going to join together. That is, chloride ion is going to leave, hydrogen ion is going to leave as well. They're going to form HCl, and this vacant space will be filled by the NH2 joining this molecule. So you're going to form your amide linkage. So HCl is going to be eliminated, and you're going to form a bond of C double bond O and NH. So this is your amide linkage, right? Fair enough. So that is ethanol reacting with ammonia in short. Now ethanol reacting with primary amine, that is one of the H atoms replaced with a R group, that is CH3 or can be anything. So now what's going to happen over here is the H again is going to react with Cl, form HCl, and all of these are taking place at room temperature, and it's going to form amide linkage. HCl is removed, and this CO joins with this NH, forming the amide linkage. Now the previous case, the name of the structure we formed was ethanamide, a simple ethanamide. 2 carbon atoms, hence ethane amide due to this amide linkage. Now over here, what's going to happen is we call it N-methyl ethanamide. Why we call that? I'm explaining. Wait. So this is going to be your methyl structure. This is your amide linkage, and due to the 2 carbon atoms, it is going to be ethanamide. So there is one methyl group attached to this N, hence N-methyl ethanamide due to the 2 carbon atoms. So we call it N-methyl ethanamide. Fair enough. And there's also a byproduct HCl, which is why it's called condensation reaction, right? Fair enough. So this is your reaction with ethanol chloride and primary amine. Next up, we'll look at how to react ethanol chloride and a secondary amine, where these two are occupied by 2 R groups. That is, any structure can be attached to the N, that is nitrogen, right? This is your secondary amine, that is 2-degree amine. Fair enough. Again, at room temperature, what's going to happen is H and Cl form a bond, forming HCl, and when these two are eliminated, you're going to form a bond with C double bond O, and this N bonded to 2 methyl structures. So it's going to form again the amide linkage, that is N bonded to C, bonded to double bonded to O. So again, over here, what you're going to notice is this, your amide linkage, 2 carbon atoms, it's going to be ethanamide again, right? However, it is going to be NN dimethyl ethanamide. Why NN dimethyl, you ask? Because one methyl connected to the N, another methyl connected to the N. Hence, NN dimethyl ethanamide due to this structure. Fair enough. So this is your way to form amides from ethanol chloride and amines, right? So you can form your amide from what? From amine, any sort of amine, or ammonia and ethanol chloride. So acyl chlorides. Fair enough. Now, in short, we looked at how to form the amide, right? Now we're going to look at how the mechanism is going to work for each of those cases. It's pretty simple. First one, ethanol reacting with ammonia. You have the same thing happening once again as with the previous examples. You can skip if you want, if you have gotten the good idea, but I'll still explain. What's happening is this carbon atom, again, is partially positive. Why? Cl pulling electrons, O pulling electrons, partially positive. This oxygen will have a partial negative charge, hence, since pulling electrons, this ammonia is going to be your nucleophile. Why? Lone pair of electrons. Notice. Draw the lone pair of electrons, make it attack the carbon, positive carbon atom, and this double bond will be removed. Why? Because new bond is forming, hence double bond removed. And in the intermediate, what's going to happen is this carbon atom is bonded to four molecules or atoms, and this oxygen atom wants to reform its double bond since it has a negative charge and a lone pair of electrons ready to bond with the carbon atom. And the Cl atom, to allow that, is going to leave the structure as a chloride ion, is going to take 2 electrons from the molecule and leave as chloride ion. And also, since this nitrogen is positive right now, why, you ask? Because it donated 2 of its electron to form a bond with the carbon atom, right? So it formed a dative bond over here. However, to allow for the nitrogen atom to be neutral, this hydrogen atom will provide the 2 bonding electrons to the nitrogen atom, right? And is going to leave the structure as H+. Now, what's going to happen is both of these are going to form a bond, forming what? Forming HCl. So, condensation reaction. And at the end of the day, you're left with what? Ethanamide. You're left with ethanamide. This is how the bond is forming. Take a look at the mechanism. Take a look at the white arrows. That is going to be the important part when answering the question. So, this is your intermediate structure. Step 1, you added the nucleophile. Step 2, you eliminated the chloride ion. Fair enough. Second example, quickly, let's look at it. Same thing is going to happen. The only difference is this nitrogen atom is now attached to the CH3. That is going to change nothing. And the rest of the structure is going to be exactly the same. However, at the end of the day, the product is only going to be N-methyl ethanamide. That's the only difference. Other than that, all the mechanism is going to remain absolutely the same. Second, by the way, so what's going to happen is when you're left with HCl and you have excess of NH2CH3, and while reacting this ethanol chloride with your, what do you call it, this is primary amine or 1-degree amine. When you have this in excess, what's going to happen is this is going to react with our product, HCl. And you know amines are what? They are base. They are what? Base. So you have your base, you have your acid, right? This base is from the reactant and this acid is from the product, right? And when you have this in excess, acid-base reaction is going to take place and is going to form a salt. This is called methyl ammonium chloride. So this is your methyl ammonium chloride salt, or called ammonium salt, right? So when you have this in excess, what's going to happen? It's going to react with the product HCl, forming ammonium salt. Keep that in mind, might be helpful. Now the second case is reacting with secondary amine, that is ethanol reacting with secondary amine. What's going to happen? Nothing is going to change, the same thing. That is, you have 2 R groups attached now to the N, and now what's going to happen is it's going to again attack the partial positive carbon atom, double bond breaks, double bond reforms, and Cl leaves. This H now is going to donate its bonding electrons and is going to leave as H+, and is going to form this beautiful dimethyl ethanamide, N-dimethyl ethanamide. Now, one thing to note over here is you may be asking, does it react with tertiary amines or 3-degree amines? No, it doesn't. Why, you ask? Because in that case, notice this would be replaced by what? CH3. So would there be any H atom to donate 2 bonding electrons? No. Since the CH3 will not want to leave the structure by donating its 2 bonding electrons. Hence, the tertiary amines wouldn't react really. I'm not really sure if there are other conditions to make that happen. However, as per your syllabus, it is up till secondary amines as far as I've seen. Fair enough. Again, the same thing is going to happen in this case as well. How, you ask? Because the HCl is going to react with the secondary amine, that is secondary amine of the reactant, and HCl of what? HCl of the product. So both of these react and form what? Salt. Goes through acid-base reaction and is going to form dimethyl amine hydrochloride, right? Hydrochloride. Now, in previous case, what happened was this was NH3, which is why you called it ammonium chloride. In this case, you have NH2, which is why it's called amine hydrochloride. You don't exactly need to know the name, you just need to know that an ammonium salt is formed, and this is going to gain what? Base is going to gain a hydrogen atom. That's all you need to know. So it gains a hydrogen atom, right? And forms a salt, right? It forms what? It forms a salt. In previous case, again, it gained what? A hydrogen atom and formed a salt. That is all you need to know for the mechanism of amide formation. That is, again, how do we form amide? From ethanol chloride or any sort of chloride, not chloride, I mean any sort of acyl chloride reacting with amines. That can be ammonia, primary amine, or secondary amine, all three. Fair enough. That is how you form the amides. No specific condition is needed in this case because both are quite reactive. Ethanol is going to be quite reactive as well, which is why this happens at room temperature. Fair enough. That is your mechanism. That is all you need to know. And we are towards the end of this section. And the last thing I'll talk about is ease of hydrolysis, right? The ease of hydrolysis, for some reason, I've added an atrocity of information over here, but I'll try to explain this in short. Ease of hydrolysis, we're going to compare mainly three types of compounds. That is aryl chlorides, acyl chloride, and alkyl chloride. If you don't know how each of those are going to look, these are the examples. This is your aryl chloride. This is your acyl chloride. And alkyl chloride is going to be, you should know this by now, this. Fair enough. So hydrolysis of acyl chloride, alkyl chloride, and aryl chlorides. Now, ease of hydrolysis of alkyl chlorides. In case of alkyl chlorides, notice one thing, the carbon in the alkyl chloride is only attached. Just take a reading of this. I don't want to explain this too much because I want to focus on the reactions, but I'll try to explain slightly. Anyways, so the carbon in the alkyl chloride is only attached to one electronegative atom. That is what? The chlorine atom, right? And the strength of CCl bond is going to be quite strong due to the carbon in CCl bond having a highly negative charge due to the electron donating effect of the alkyl group. This alkyl group is going to have an electron donating effect, which is why carbon has a high negative charge, due to which the CCl bond is strong. So the CCl bond is quite strong, making it less reactive, right? Making it what? Less reactive, because the CCl doesn't want to leave the structure. Now, the alkyl chloride are less reactive because of this stronger bond of the CCl, because C is providing the electrons due to the alkyl structure added to it. Now, the chlorine, try to remember, is very electronegative. So it will go anywhere where it can gain the electrons, right? It wants a higher density of electron. Now, the carbon atom is being able to provide what no one else is. That is high negative charge, right? Fair enough. Okay. Now, in case of hydrolysis of alkyl chlorides require a strong nucleophile like OH minus to hydrolyze the alkyl chloride. Hence, NaOH is used and is refluxed with them. So, understand that the CCl bond is very strong, which is why you need a strong nucleophile. In this case, OH minus. Now, if you added H2O, that wouldn't be a strong nucleophile because the negative charge on it is not that strong due to it being a partial negative charge on the H2O. In case of OH, it has a stronger negative charge, hence it acts as a better nucleophile, which is why you need to add NaOH and reflux with it to have hydrolysis take place. So that is ease of hydrolysis of alkyl chloride. Next, let's quickly look at acyl chloride. So this is your reaction of alkyl chloride, This is your reaction of alkyl chloride. This alkyl group attached to the chlorine atom reacts with what? NaOH in the condition of heating, that is refluxing, and you're going to form what? This alcohol and NaCl. That is your hydrolysis. Fair enough. Now, quickly, acyl chloride. What's going to happen? Acyl chloride, there is a high electronegativity difference between what? The carbon and the chlorine atom. So let's read. The carbon in the acyl chloride is attached to chlorine atom and double bonded to oxygen atom. So both of which are really electronegative and pulls away electrons from the carbon atom. making it highly positive and highly reactive. So understand this. In case of ethanol chloride, propanol chloride, anything, any sort of chloride, what's going to happen is this oxygen atom is pulling electrons away. This chlorine atom is also pulling electrons away, making it highly positive, and both of these highly negative, right? So in this case, the difference in charge between both is really, really high, due to which it is easy to break the Cl atom and carbon atom off. So this forms an electrophile that is, as you've seen already, talked about in this video, electrophilic addition reactions and all that, substitution reactions. So what you saw is this is going to be your electrophile, positive charge, and the Cl is going to break off as chloride ion, right? So in this case, the ease of hydrolysis is greater. Now the strength of CCl bond due to highly positive C and Cl bond makes it easy to react in room temperature and is easily hydrolyzed, making it a weak CCl bond. So the hydrolysis of acyl chloride is rapid and does not require any further condition for the reaction to take place, right? So this is going to take place at room temperature. H2O you add room temperature. You may heat if you want the reaction to be faster, but not needed, and it's going to form your carboxylic acid and HCl. Fair enough. This is your ethanoic acid. This is your HCl. Great. This is your hydrolysis of what? Acyl chloride. I'll also mention one more thing. What if the question asks you, I haven't seen this, but what if the question asks you CH3, CH2, C double bonded to O and Cl, which is which is easier to hydrolyze between ethanol chloride and propanol chloride, which is easier to hydrolyze? You're going to say this one is easier to hydrolyze. Why, you ask? Very simple. The positive charge on this is lower compared to this one. This has a higher positive charge. Why, you ask? Because this alkyl group is going to do what? It is an electron donating group. So the positive charge on this carbon atom decreases. Does what? Decreases. And over here, the positive charge is really high due to both of these electronegative atoms. However, over here, there's only one CH3 group. Over here, there are two carbon atoms pushing electrons into the carbon bond. So you have a highly positive, less positive carbon atom. Hence, this is easier to hydrolyze. Compared to what? Compared to propanol chloride or other long chain alkyl group attached, right? Next up, last one, aryl chlorides. I've already talked about the strength of aryl chlorides in the Arenes section. So again, what's going to happen in this case is the electronegative difference. If you want to look at it, the carbon in aryl chloride is attached to chlorine atom and also has a partial double bond feature. Keep this in mind, very important, has a partial double bond feature with the chlorine atom. Due to the p orbitals of the chlorine atom and the carbon atom overlapping, there is a partial double bond feature. Now, the chlorine has a p orbital overlap with the benzene structure, resulting in losing a lone pair of electrons into the aromatic ring. This ring structure is going to pull the electrons from the chlorine atom. Hence, the negative charge is going to dissolve into this entire structure. Keep that in mind. So this results in the partial double bond feature. Now the strength of CCl bond. Due to the partial double bond feature, the CCl bond is the strongest of the three. Why, you ask? Because of the double bond feature, right? So due to the p orbitals overlapping double bond feature, hence really strong and really hard to break, right? Fair enough. So in this case, due to the strong CCl bond, hydrolysis will not take place, unfortunately. Hence, the strongest CCl bond, hardest to hydrolyze. In this case, strongest CCl bond, right? So this is hardest to hydrolyze. This is easiest to hydrolyze. Acyl chloride, easiest to hydrolyze. And in the middle, you have alkyl chloride. Compared to, let's say, acyl chloride, in acyl chloride, there is a greater charge difference, which is why it is easier to separate the bond. In case of alkyl chloride, there is an electron donating group, right? The difference in charge is less, which is why it is slightly harder to break the bond. However, this is the hardest in aryl chloride. Why? Due to the partial double bond feature. And that is going to be it for this section. And next, we're going to talk about what? We're going to talk about nitrogen compounds. So, yeah. Now, the last section, this is nitrogen compounds. And after this, we're going to be done with all of organic chemistry. So let's quickly finish all of it. Heads up, what are the types of nitrogen compounds? First, primary amine, one of the H being replaced by CH3, forming a 1-degree amine. Second, secondary amine, that is 2-methyl group attached, dimethyl amine, so 2 degree. This amine, 3 degree, 3 CH3 bonds, replacing the H. This is another nitrogen compound called a nitrile, and since 2 carbon atoms, this is going to be called ethane nitrile. This is your nitrile functional group. And this is your amide, which we will be closely working with. So this is your amide linkage. You probably already know from carboxylic acid unit. And this is your secondary amide. That is, one of the H has been replaced with what? CH3. And will be called N-methyl ethanamide. This was ethanamide. This is N-methyl ethanamide. Over here, both the hydrogen has been replaced by CH3, forming NN, that is 2-methyl dimethyl ethanamide. Still ethanamide due to 2 carbon atoms. Fair enough. So first up, we'll talk about producing amines, right? How can we produce amines? There are a couple of ways to do it. First, reacting halogenoalkane with ammonia and form amine. Nucleophilic substitution reaction will take place where the ammonia acts as the nucleophile, replacing the halogen. So excess ammonia, hot, ethanolic ammonia under pressure is needed. Keep these conditions in mind because you're going to need it. You have your chloroethane, you have your ammonia in excess. This HCl is going to form, as usual, HCl. And this N is going to join with this C, that is this carbon atom, and is going to form ethyl amine. This is your ethyl group attached to amine group, ethyl amine, HCl. No mechanism for this is required. So in general, just understand this HCl is going to leave the structure and form amine. This is your primary amine since N is bonded to 2 hydrogen atoms. Now, when limiting amounts of halogenoalkane is used, this is limiting, we get primary amine. That is, our reaction stops at primary amine. That is, you're going to get NH2 attached to the ethyl group, and that is where the reaction ends. However, if halogenoalkane is in excess, further reaction will take place. How, you ask? See this. So, I mean, in general, for the ammonia, it was already in excess, so this is important as well. When forming primary amine, the ammonia was excess, but your chloroethane was limiting. That is, the reaction stops at forming ethyl amine. But if both are in excess, ammonia is in excess and chloroethane is also in excess, what's going to happen is first your ethyl amine will form, that is as seen above over here. That is, chloroethane reacts with ammonia and forms ethyl amine, so that part stays the same. However, due to excess chloroethane, further reaction takes place with the product. So this ethyl amine reacts with chloroethane. Since we have put chloroethane in excess now, the product ethyl amine reacts with reactant chloroethane. What's going to happen? Your ethyl amine has 2 hydrogen atoms, so it's going to react with the chloroethane. That is, it's going to form HCl, and this N joins this carbon atom, forming second degree amine. R group, right? Fair enough. So this is how you form second degree amine, secondary amine or diethyl amine. This is your ethyl group, and allyne. And you also form HCl. Now, since it is in excess, your reaction will move on further. That is, you're going to form tertiary or triethyl amine. How you ask? This H and Cl will form HCl. This N bonds with this C, forming triethyl amine. So this ethyl group attaches to this nitrogen, while there are already two ethyl group from this previous product, right? So putting this over here and this over here. So that is how the reaction is taking place, and this is how you will form your amides. No specific reaction conditions needed, but all these. So you don't need any, different condition for what you call it, secondary and tertiary. It is going to stay the same as forming primary amine. The only difference is your reactant, both the reactant need to be in excess. So if your chloroethane is also in excess, then yes, you will form secondary and tertiary amine. But these conditions you need to keep in mind, that is excess ammonia, hot ethanolic ammonia under pressure. So keep these in mind for both, all three of the reactions. Anyways, the second way to produce amine, that was one way to produce amine, that is reacting with halogen and alkyl. The other way is reduction of amides. You know already how to form amides from the carboxylic acid carboxylic derivative unit. So in case of reduction of amide, if you reduce the amide, that is the C double bond O, if you reduce that, we're going to form amine. Interesting. Let's see. We can reduce amides to form amines. Both primary and secondary amine can be formed depending on the amide reacting. Let's see how that works. Now to do this, you need LiAlH4, lithium, aluminum hydride in dry ether. Dry ether, why? Because this is going to produce H2O. So to remove the moisture, you're going to need dry ether. Dry ether in general is very dry, so it's going to absorb the moisture. So yeah, that is the purpose of using dry ether. And lithium aluminum hydride is your reducing agent. You know it from AS. So this is your primary amide linkage. This is since two carbon atoms, ethanamide. And when you reduce this, only this part is going to be affected. Keep that in mind. C double bonded to O is going to be affected, and it is going to be reduced to what? To H. CH3 stays as it is. NH2 stays as it is. Just the O is going to be removed and is going to form H2O. And you're going to add H over here. Okay, so two of the hydrogen atoms is going to add one over here, and the rest two is going to form water molecule, H2O. So that is how we can form ethyl amine from amides. That is, in this case, I'm taking primary amide, reducing it, and forming ethyl amine. That is primary amine. Now, if I want to form secondary amine, let's say dimethyl amine, not dimethyl amine, sorry. In this case, since I'm taking an ethyl group, and methyl group is going to be an ethyl methyl amine. So in our case, in general, if you want to form, let's say, secondary amine, what you're going to do is you're going to take a secondary amide. What are secondary amides? Basically, one of the H is going to be replaced by R group or CH3 group. So this is your secondary amide where N is bonded to only one hydrogen atom. So over here, what's going to happen is same thing. The oxygen part is going to be reduced to what? C bonded to H. Right? So at the end of the day, when you reduce it, you're going to add one H over here, one H over here, and the two other H is going to form H2O. We add 4H to balance the equation. So at the end of the day, what you're left with is typically CH3, CH2, N, H, CH3. Ethyl group bonded to N and a methyl group bonded to N and H group. So what do you understand from here? You're understanding it's a secondary amide. One ethyl, one methyl, and one isolated, individual hydrogen atom. So we call it N-ethyl methyl amide. Fair enough, the name is not important, I just added it. Now the same can be done with tertiary, that is, if you have a CH3 over here, same thing is going to happen. You're going to have a CH3 over here as well. Nothing else changes. So that is how you form amide from the reduction of amides. Very simple. All you need to know is you need lithium aluminum hydride in the presence of diethyl. Next. Another way, third way, is reduction of nitriles. As seen, this is your nitrile group. And now if you reduce this, you can also form amides. The C triple bonded to N group is reduced to NH2 group. There are two ways to do it. That is, to reduce it, you can opt for two ways. One is CN, cyanide gas reacting with H2 and nickel catalyst. That is, the cyanide, this in gaseous form is going to react with H2 in the presence of nickel catalyst. That is this one, I guess. Yeah. So the ethane nitrile in gaseous form is going to react with H2 in the presence of nickel catalyst. As a result, this part is going to be reduced to forming a single bond only, along with the two hydrogen bonds. Okay? So it's going to add two hydrogen atoms, and is going to reduce this to one bond only. Okay, so this is one way, that is using hydrogen gas. The other is again using lithium aluminum hydride. So in general, knowing that the oxidizing and reducing agent is going to help you a lot. Reducing agent, as you know, is lithium aluminum hydride, and in the presence of this reducing agent, this bond is going to be reduced to NH2. The triple bond breaks into one. So that is how you turn ethane nitrile to ethyl amine. Fair enough. Last way to do it, I see this come quite often, and this is basically reduction of nitrobenzene. This NO2 attached to the benzene structure can be reduced. That is, in the presence of SN10 and concentrated HCl, and you reflux or heat the mixture, and you're going to get NH2 and 2H2O. So to balance the equation, we add 6 hydrogen atoms such that 4 over here, 2 over here, one forming the phenylamine, the other forming 2 molecules of H2O. So we are reducing NO2, nitrobenzene, to phenylamine. Right. So the conditions are reducing agent, any reducing agent, ideal lithium aluminum hydride, tin concentrated HCl, and heat the mixture. Next thing, we're going to talk about how to form amides. We have already talked about this in the carboxylic acid and derivative unit. So you probably already know how to form amides. That is, from ethanol, we can easily form the amide, right? Fair enough. So you probably already know it. So moving on to the third part, that is Basicity of nitrogen compounds, amines, and ammonia. Basically, what does basic nature mean? Ability to attract H plus ions, right? This ammonia, if it has a higher negative charge, higher electron density, it will have a higher tendency or larger tendency, or it will be easier for it to gain back this hydrogen ion. Agreed? So if it has a greater negative charge, it is more what? Basic. That is the simplest way I can explain it. And if it has a lower negative charge, it will be harder for it to gain back the H plus. Yes. Depending on that, you can make your judgment whether or not one is a good base or a weak base, right? You can also read the book to get a better idea of the examples, but this is where I'm going to keep this at to move on to the reaction specifically. But if you understand how dense the electrons are on the nitrogen, you will be able to decide it for yourself. Fair enough. Next part, producing phenylamine. So you saw how we produce phenol in the hydroxy compound unit. Now you're going to see how to form phenylamine. It's pretty simple, but a lot of conditions to remember. But there is overlap of conditions over here as well, so don't worry. Now to produce phenylamine, that is this is your phenylamine, amine group added to benzene structure. Now, step 1, you're going to carry out nitration of benzene. Benzene structure, nitration, you know it already from the first unit of this video, that if you have nitric acid, H2SO4, forming nitronium ion, this is going to carry out electrophilic substitution reaction, and in the temperature of 25 degrees Celsius to 60 degrees Celsius, it's going to go through electrophilic substitution, forming nitrobenzene. Great. Step 1, we formed nitrobenzene. Next one, this nitrobenzene has to be reduced. Do you know how to reduce this? Yes, you know. How? Because we just talked about this. NH2. So, in the presence of hot tin, SN, concentrated HCl, and reflux, we are going to form NH2. That is a phenylamine, right? Now, you will ask, why the H3+? This is not what I'm used to. However, the thing is pretty common sense, that since it is HCl and you know phenylamine is basic in nature, right? It is alkaline. So it's going to attract the H+, which is why it's going to form this phenylammonium ion, right? This is again acidic, since it will now be able to lose H+, right? So it first forms phenylamine. Now, due to the acidic condition, is going to form the ammonium ion. Okay. Now, step 3, this mixture is made alkaline. Why? Because you want this, right? So to get rid of the NH3+, what's going to happen? You're going to create an alkaline solution, right? So add NaOH and it's going to form your good old NH2, which you are used to. Now, phenylamine is separated by steam distillation process. So you basically carry out steam distillation process to separate it from H2O and the entire mixture. So phenylamine is separated by steam distillation and you get pure phenylamine. So 3 steps: nitration, then reduction of the nitrobenzene, then make an alkaline solution to get phenylamine. Now, fifth thing we're going to talk about is reaction of phenylamine. Similar to other groups, other electron donating groups, it's going to activate these position 2, 4, 6 position. In case of bromination, you will have aqueous bromine. It is going to go from orange to colorless. The reaction has gone to completion. So this Br plus 3Br plus is going to replace H plus in 3 position 2, 4 and 6, forming 2,4,6 tribromophenylamine. And also HBr. I don't know why I didn't write it, but to balance you have to. So 3HBr. And the main product is 2,4,6 tribromophenylamine. So this one, you already know it from the previous section, but I'll still talk about it. That is forming diazonium salt from phenylamine. How to form diazonium salt from phenylamine? You're going to take the phenylamine and how to produce it. You already saw from here how to produce phenylamine. So you're going to take that phenylamine and react with HNO2, that is nitric acid, and keep the temperature below 10 degrees Celsius. Add HCl and diazonium salt will be formed. Okay, so again, HNO2 is not stable, which is why we try to make it readily. That is, we can react NaNO2, sodium nitrite, and HCl to form what? HNO2, that is nitrous acid and NaCl. You already know this, but I'm repeating it because it's repeated in this chapter again. So yeah, phenylamine reacts with HNO2, which is readily made in this step. And in the presence of acid and temperature below 10 degrees Celsius, you're going to form the salt. That is diazonium salt. Right? And also 2H2O. Because these will form 2H2O. Great. So that is diazonium salt formation from phenylamine. Next up, azo compounds. So you already partly know how to form azo compound from previous unit. That is phenolic compounds. Again, I'll talk about this with another example, that is formation of orange dye. Previous one, I guess, we talked about the yellow dye, but this one we'll also talk about the orange dye. Now, how to form azo compound. Azo compound will have functional group N double bonded to N. Now, we'll be studying about aromatic azo compounds. There are also aliphatic azo compounds, which is less common. Now, what does all this Hebrew mean? Basically, aliphatic means linear chain, and not exactly linear, but these long chain hydrocarbons, CH2, CH3, stuff like that. These are aliphatic. And when you have these are aromatic compounds, right? Benzene structure, hydroxy compounds, these are all aromatic structures, ring structures. Fair enough. So, right now, in case of azo compounds, we are going to talk about with respect to aromatic azo compounds. That is, you'll see these, what do you call it? Hexagonal structures. And these are going to form the NN azo group. That is your azo compound, right? Fair enough. So how to produce this diazonium compound? We are going to go through coupling reaction of diazonium ion and alkaline phenol. So previous one, you did study it, but you didn't know this was called coupling reaction. Now you know. So this is called coupling reaction, where the diazonium ion is going to react with alkaline phenol, Y-alkaline, as you know, making it a better nucleophile, more reactive as well. So in general, azo compounds are used as dyes. You can see orange dye and also yellow dye. So yeah, for preparing orange dye, we're going to go through coupling of benzene diazomium chloride and phenol, but in alkaline condition. Now, we are first going to form our nitrous acid, that is HNO2. We're going to react NaNO2 HCl form HNO2, that is nitrous acid. You probably have already memorized this from so many times. But yeah, sodium nitrite, HCl reacts forming HNO2 and NaCl. Now, diazotization, phenylamine now is going to react with HNO2, that is what we freshly prepared, and HCl within a temperature between 0 and 10 degrees Celsius, and it is going to form your unstable benzene diazonium chloride salt, and also two water molecules. Now, the coupling reaction is going to take place where electrophilic substitution is going to take place, where the diazonium ion is an electrophile. So this I didn't talk about in the previous section, but basically, as mentioned, this N has what? Is positive, right? Now, due to 4 bonds, which is why it acts as the nucleophile, and it is able to remove the H plus over here, that is directly opposite to the OH. So this H plus over here is replaced, and a bond is formed, and that allows. So this Cl will be removed. This Cl will be removed, and this nitrogen is going to form a bond with this carbon atom, forming your azo compound. So this this bond will be broken. This positive charge is removed, and now after the Cl is removed, this is now going to have a positive charge. Hence, this compound now acts as the electrophile and is able to go through electrophilic substitution reaction. You don't need to know all of that, but in general, that is what happens. So electrophilic substitution reaction takes place. So hydrogen atom replaced, and this bridge is added between this group, this salt group, diazonium salt, and phenol. Fair enough. So notice one thing: you'll often be asked to write down the constituent compounds that form the azo group, this azo compound. Now, from this, you can easily say that this is going to be one group and this is going to be one. So you can say the constituent compounds or reactants were one phenol and the other benzene diazonium salt, right? This is your benzene diazonium salt, and the other is a phenol. So just break the bond from over here, and you'll get your answer that what the constituent elements, compounds were. And oh, by the way, you also get HCl due to this. Fair enough. Now, NaOH is used to neutralize the acid produced. That is this. That is why alkaline conditions are used. And yeah, fair enough. So, oh, by the way, in this case, for the first step, we produce the HNO2. Second step, we produce the N triple bonded to N, and third step, we are carrying out the coupling reaction. And I guess I had mentioned that this NaOH is used to create a phenoxide ion or to make this a better nucleophile. If I said that, I was wrong. I just realized. But that since I got used to saying that phenoxide ions are better nucleophiles, so I guess I said that. But over here, it's not that case. The reason you use NaOH is not to create the phenoxide ion or not to create the nucleophile. The main purpose is to neutralize this acid produced and create this azo compound. So over here, there is no nucleophilic reaction taking place. There is electrophilic substitution taking place. That is where this is the electrophile. So if I said that, I'm sorry. But yeah, this is basically the entire reaction. This is why you use alkaline conditions, right? Yeah, fair enough. So, okay. And this ion is going to be the electrophile, and it's going to substitute H at the fourth position. Yes, fourth position substitutes the H atom, and the delocalization of electron happens throughout the azo compound. due to the N double bond to N bridge. Since it is more stable, as mentioned, due to the double bond, the electrons are going to be delocalized throughout the entire structure, hence more stable. Fair enough. Now, previous case, we saw how to form this compound, that is an orange compound, that is an orange dye. And now we're going to see how to produce a yellow dye, that is, it just has two branched CH3, nothing else. So the coupling of benzene diazonium chloride and C6H5NCH3 but 2. So 2 methyls attached to N. 2 methyl attached to N. So in this case, what's going to happen is, take a wild guess where the where the hydrogen atom is going to be replaced. If you guessed this, you were accurate. If you guessed this, you were wrong. Anyways, so this hydrogen atom is going to be replaced. So exactly opposite to the functional group. So this H atom replaced, electrophilic substitution takes place, HCl is formed, and this bridge is going to be formed over here, right? Fair enough. This NN double bond acts as the bridge, 2 methyl groups, and you have your yellow azo dye. So in the previous case, I don't remember if I drew the orange dye or the yellow dye. Let me check quickly. So yes, it turns out I did make a mistake. This is not going to be yellow PPT. This is actually orange. I don't know why I wrote this as yellow. Oh, yellow orange PPT scene. So I didn't mention it. Anyways, it's basically going to be orange PPTs. But yes, you can call it yellow orange PPT. Anyways, moving back to the nitrogen compounds. So when you have N connected to 2 methyl groups, it is going to be yellow azo dye. And when you have OH, it is going to be orange azo dye, or yellow orange, whatever you want to call it. So this is your coupling reaction, the two coupling reaction to form azo compounds. Fair enough. Now we're going to move on to reaction of amides. Okay, so first up, we're going to talk about hydrolysis of amides. Hydrolysis can be done through reflux with acid or alkali. So you can go through acidic hydrolysis or alkaline hydrolysis. If gone through acidic hydrolysis, you're going to form ethanoic acid and NH3, where due to acidic nature, this NH3 is going to gain H plus, forming NH4 plus. Now, in case of alkaline hydrolysis, you're going to form carboxylate ion. That is, due to alkaline conditions, H plus will be lost, right? H plus will be lost, and your NH3 is going to stay as it is, since it is what? It is a base, right? So it is going to stay as it is. And since there was an acid, this acid actually lost the H plus, unfortunately, to NaOH, forming what? Forming H2O as well. Anyways, so when you have acyl or acidic hydrolysis, your acid stays as it is, and your base is going to gain H plus. When you have alkaline hydrolysis, your acid is going to change into salt, or carboxylate ion, and your base stays as it is. Now, the same thing can be done for secondary amides as well, right? When you have the secondary amides, nothing changes. Basically, instead of the H over here, you would have a CH3 group, nothing else, right? So if you had tertiary, same thing, 2 CH3 groups and 1 H group, nothing else. So the same thing for secondary or tertiary. Now, the reduction of amides we already talked above, that is how to form amines. So if you reduce the amine, you're going to form amine. Fair enough. Now, this part, we're going to talk about zwitterions, that is basically amino acids. So these amino acids are going to form zwitterions. So amino acids can form zwitterions since it has 2 functional groups. If you don't know what zwitterions are, I'm going to talk about it. But first, understand what amino acids are. Amino acids are groups of compounds which has both carboxylic acid group and your amine group. So this is basic in nature. This is acidic in nature. So it has both acidic and basic structures, which is why it is amphoteric. Amphoteric, if you forgot, is both an acid and base. So this is both an acid and an base. Now, in case of amino acids, there are 20 main types, which are building blocks of protein, I guess. I don't have biology, so I don't really know. But in general, amino acids are going to only vary in this R group. So this R group is going to change. Let's say this is the R group, or this is the R group, or let's say this is the R group, or this, or this, or this. So the R group is going to basically change, not anything else. So you're going to still have H, you'll still have COOH, you'll also have the amine group. All those three stay same, but with different amino acid, the R group changes. That's the only thing. Now, due to both amine and carboxylic acid, it is going to go through amine plus acid reaction, that is base plus acid reaction. And it is also going to go through carboxylic acid plus base reaction, that is NH3. So yeah, this is your base. This is your external acid. And this is your carboxylic acid of the compound, that is amino acid. And this is external base. So it goes through both acid-base reactions. Okay, so to form zwitterions, it's basically going to intramolecularly react. Hence, this H is going to go over here. This gains H plus ion, and this loses H plus ion, forming COO minus and forming NH3. And this plus 1 and minus 1 is going to form a zwitterion. This is called a zwitterion, where intramolecular exchange of H plus takes place, and there is one COO minus and one NH3 plus. Now, due to this zwitterion formation, they're going to have strong intermolecular forces due to electrostatic forces of attraction. Positive attracts negative, hence strong intermolecular bonds. This is also why they're going to dissolve in polar substances, right, like water. So they're going to be easily soluble in water, right? So amino acids in general are soluble crystalline solids, right? Fair enough. Now the isoelectric point. Let's understand what the isoelectric point is. When amino acids are going to dissolve in water, they exist as zwitterions. Due to acidic and basic properties, they act as buffer solutions of COO3 and NH3. In buffer solutions, you know, it resists small changes in acid and bases. So basically, when you add acid, it is going to gain the H plus. Like, for example, over here, if H plus is added, the COO minus gains it and forms COH. And if OH is added, the NH3 is going to lose H plus, forming water and NH2. So that is how it resists the changes in H plus or OH concentration. So amino acids now will have a net positive charge due to gaining this H plus, right? Due to gaining H plus, it now has a net positive charge. In case of OH added, it's going to have a net negative charge, right? Since H plus was lost, forming H2O. So consider both of these cases, understand what's happening. In one, H plus gained, in the other, the H plus removed, right? Fair enough. So take a look at this, understand it properly, what's going to happen. Basically, the zwitterion is going to react, right? And acts as a buffer solution. So the zwitterion resists small changes in pH. Now we see that upon adding acid or base, the zwitterion can be positive or negative. Keep that in mind. Now, different amino acids, the pH needed to be adjusted such that the zwitterion remains neutral is different. And this pH is the isoelectric point. What on earth do I mean by that? Basically, notice one thing. For a specific concentration of H plus, it is going to remain as this. Or let's say, until and unless you increase the H plus to a certain pH, it is not going to be positive until and unless you add a certain concentration of H+, that is, until unless you decrease the pH to something, it is not going to turn into a positive ion. So therefore, if you find the isoelectric point, that is, let's say the isoelectric point of this Zwitter ion is going to be 6.5. If you reduce the pH, that is, you add H+ concentration, it is now going to be positively charged. If you increase the pH, decrease the H+ concentration, therefore increase OH concentration, in that case, there would be a negative charge. So for all Zwitter ions, there is an isoelectric point. For, let's say, this one, it is 6.5. At 6.5, it remains neutral, 1 negative, 1 positive. So it is neutral in charge. So for all Zwitter ions, there's an isoelectric point. For this one, it could be, let's say, 7 or 8, let's say. So you have to add, let's say, H+ to give it a what? Give it a positive charge. And you had to give it OH ions to make it more negatively charged, or give it a -1 charge. Hence, every Zwitter ion has a specific isoelectric point at which it remains neutral. So for it to remain neutral, that is, have a negative charge and a positive charge, +1, -1, it needs what? It needs a specific pH. Fair enough. So if the OH concentration increases more than your isoelectric point, your Zwitter ion becomes negatively charged. If pH decreases, that means higher concentration of H+, then your Zwitter ion becomes positive since it gains the H+. Fair enough. That is in short what isoelectric point is and Zwitter ions are. If you want more details, you can check the book, but I guess this is somewhat enough. But you also need to understand, I guess, electrophoresis or something, that is in analytical chemistry. You have to, I'm not going to talk about that in this video since it is sort of a part of analytical chemistry. You need to check it out from the book. But yeah, electrophoresis in general has to work with isoelectric point and Zwitter ions. Anyways, moving on to the next part, that is peptide bonds, right? Peptide bonds in general is basically when reacting amino acids with amino acids, you're going to form this peptide bond. That is C double bonded to O and N bonded to H. You probably know this as amide linkage, but this is also called your peptide bond. Anyways, even in case of forming peptide bonds, it is a condensation reaction just as amide linkage. So for forming the peptide bonds, a condensation reaction is going to take place between amino acids to form a peptide bond. So the reaction between two amino acids is going to form this peptide bond. And since there are two amino acids, it is called a dipeptide with one peptide bond. So what's going to happen is we have one amino acid and another amino acid. Consider both of these to be same or different, doesn't matter, because the only difference between two different amino acids is going to be the R group, nothing else. So this carboxylic acid group reacts with this H group of the amine and forms H2O, and is going to form this peptide bond where the C double bonded to O reacts or connects to NH, right? Forming the peptide bond. And this is called a dipeptide. This entire molecule is called a dipeptide. Two amino acids, hence dipeptide. Now, two dipeptides or not two dipeptides, but one of the dipeptide can react with another amino acid and is going to form a tripeptide. That is, three amino acids reacting with two peptide bonds, and this is going to be a tripeptide. Fair enough. A polypeptide is those where there are more than three amino acids linked by peptide bonds, right? And if you have to identify the repeat unit, this is going to be your repeat unit. This is also repeat unit. This is also repeat unit. Fair enough. So polypeptide, more than 3 amino acids and more than 2 peptide bonds. Now, last thing, I guess, hopefully, semi-last thing, polymerization. Formation of polyester, you already know this somewhat. In case of polyester, it is a condensation reaction. You're going to react diol with dicarboxylic acid. This is your diol OH. Reacts with dicarboxylic acid, COOH, COOH. This H and OH reacts to form ester linkage. This is what? Ester linkage. And this is your repeat unit. Plus 8 condensation reaction, so H2O forms. So your repeat unit is this, right? And it is going to form your ester linkage. So you're going to have one ester linkage and the 2 monomers joining together. That is your one repeat unit. Fair enough. So this is reacting a diol and a dicarboxylic acid. You can also use one monomer. In this case, we use 2 separate monomers. You can use one monomer, that is hydrocarboxylic acids. That is one hydroxy group and one carboxylic acid group. And this is going to react to form a polyester as well. So OH reacts to H, forming ester linkage, C double bonded to O, and this is your one repeat unit. You have to give extension bonds, by the way. I didn't give it, but you have to give the dotted extension bond to get the marks. H2O eliminated as well. So this is your ester linkage, and you're basically using 2 monomers of the same hydroxy carboxylic acid. Fair enough. Next, formation of polyamides. How to form polyamides? You know amide linkage, so you're going to react diamine with dicarboxylic acid. So this is how to form nylon, by the way. And in the middle, notice I'm writing R1. So basically R1 is CH2, 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 CH2. I don't have the space, so I'm writing it as R1, but I'm writing here as well that R1 is 4 CH2. And R2 over here for the diaminohexane is 6 CH2. So you understand, 6 CH2 in the middle over here. But I don't have the space, so I'm writing it as R2. So hexane, 1,6-dioic acid, and 1,6-diaminohexane, 1,6 because in the middle there are actually 6 carbon atoms, but I didn't draw it, but I did write it over here. So do understand. And this is going to react with this, forming your amide linkage over here, and this is your one repeat unit. Do draw the extension bonds to get the marks. Amide linkage, and this is your nylon. This is your nylon structure, okay? And your H2O. This is called 6,6 nylon because over here 6 carbon atoms, in the middle 4, 1, 2 plus 4, 6, and in the middle 6, so 6 carbon atoms, hence nylon 6,6. Next, forming Kevlar. You're going to use diamine and dicarboxylic acid. So you're going to react diaminobenzene, 2 amine groups attached to the benzene structure, reacting with dicarboxylic acid attached to your benzene structure. So this is going to react to form, again, condensation reaction, HOOH joins, forming H2O, and this is your one repeat unit, where this is your amide linkage. So yeah, this is your amide linkage. This NH and CO bonds together, forming this amide linkage, and this is one repeat unit. Again, extension bond should be there, and this is your Kevlar, one repeat unit of Kevlar. Last, semi-last. So for this, you're going to use aminocarboxylic acid to get a similar structure to nylons. So you're going to use one monomer to form this, that is aminocarboxylic acid. This is amino carboxylic acid where R represents 5CH2, so CH, CH, and so on and so forth, you understand. So R will be 5CH, and over here again the same molecule as this same monomer reacting together, OH and H forms a bond forming H2O, and this CO and NH bonds together forming this amide linkage. So this is your one repeat unit with the extension bonds. Fair enough. Last, formation of proteins. You're going to use amino acids only to form the protein. So I'm using one amino acid over here, another amino acid over here, OH and H bonds, this CO and NH bonds together to form amide linkage over here, or the peptide bond, and this is one repeat unit of your protein. So there's also going to be H2O. Now, if you add water to the protein, it is, it's going to hydrolyze, and it is going to break down into amino acid, that is, into its monomers. Great. So that is basically it for formation of proteins. And the last thing is basically in case of polymerization, it's basically the same thing. H2O, you're going to get H2O, peptide bond, or ester linkage, nothing else. Now, last thing, bio and photodegradability. Biodegradability is when you can hydrolyze it and it's going to degrade. In case of polyalkenes, they're made through addition polymerization, that is C double bond is broken, and this is going to form extension bonds over here, and this is going to be your polymer. Now, since in case of addition polymer, they're made through addition polymer, no water is formed, so you can't hydrolyze it back. Now, in case of polyalkenes, they're also non-polar and saturated, making them inert chemically. Hence, chemically changing them into other useful products is very difficult, right? But we can still burn it and get energy, but if you burn it, it's going to release CO2, so it's not so good for the environment, right? But in case of polyester and polyamide, you can hydrolyze it. How, you ask? You can go through alkaline hydrolysis or acidic hydrolysis. In case of, let's say, this polyamide, if you go through what? If you go through alkaline hydrolysis, it is going to break down into the monomers, that is, since it is a protein structure, it is going to break down into one monomer, that is the amino acid. So this amino acid, notice, in alkaline condition, NH2 stays as it is. So 1H adds over here, 1H adds over here. And it is supposed to be COH. However, the H is replaced by the Na. Why, you ask? Because of the alkaline condition. This Na replaces the H. Now, in case of acidic condition, the COH remains as it is, but due to the H, this N is going to gain another H, making it NH3. So that's the only difference in case of alkaline and acidic condition hydrolysis. Now, the same thing is going to take place with polyester. In case of alkaline condition, the H is replaced by Na, forming the salt. In case of acidic condition, NH2 gains a proton, or H plus, forming NH3. And last is photodegradability. So in case of photodegradability, what happens is polyesters and polyamides have C double bond O, right? And in this case, what happens is it is going to gain energy from UV light. So from the EM spectra, it's only going to get energy from UV, because that frequency allows this bond to be weakened, right? So it gains enough energy, and this C double bond O bond is weakened. So, right. So this weakens the bond, allowing it to easily break down, making it photodegradable. However, this does make the polymer weaker for repurposing it into any new use. Although yes, it is photodegradable, it is great, it is useful. You can once you have made the polymer, you can break it down into smaller structures. So it is, good that way, rather than the other polymers, that is polyalkenes, which you cannot break down. However, in case of photodegradability, yes, you can break it down. However, the overall lifespan or the use of it is decreased, because it becomes really weak. So it is more prone to any sort of damage. And that is going to be it for this entire video. I really hope this video was helpful. A lot of time was needed to make this entire crash course. I really hope it was helpful, and thank you for watching the entire video.